300 degrees. There is a black line here because we are in the brittle plastic transition for quartz, as I stated yesterday. And at 550 degrees, there is a brittle plastic transition feldspar because each mineral has its own brittle ductile transition. For quartz is 300 degrees, for feldspar 550, maybe calcite is 200 degrees, olivine maybe 800 degrees, it depends on the minerals. And you can see also on the left side the deformation in the brittle realm by linear relation between stress and strain. Up after the brittle plastic transition, you have a power law or exponential law of the quartz, like this line. In the first part, happens the same, but it is shift a little bit in depth up to this part and this one. So, for example, if you are in this part of the diagram, you have ductile deformation of the quartz and brittle of the feldspar that we observed yesterday in some myelonites coming from granites. And you can see in this picture the same that we observed yesterday. Quartz is deformed in the ductile way, and feldspar is broken with some fracture, maybe a angle fracture or similar. In this part of the diagram, Fossen and Cavalcante put the mechanism of the formation of quartz depending of the temperature, that is bulging, subgrain rotation, and grain boundary migration. So the formation show different way of deformation depending of the temperature. With increasing temperature for upper part to the lower part, you have with three different main mechanisms of deformation that I will show you in this lesson. Okay, brittle deformation is a cataclysite in metacarbonate rocks in the lesser Himalaya and western Nepal. So the formation is brittle. The rock is fragmented in cluster like this, maybe something like a cataclysite because there are a lot of fragments, a small amount of matrix. It is a completely brittle process. The rocks are broken, are fractured with no more ductile deformation. To date, it's difficult because no, it's very difficult. From scene section is difficult because you can date the fragment, so you can put a lower limit to deformation, but it is not enough because in the cataclysm you can only observe a small fragment of the same rocks, but no new minerals or some processes. So you have to use some other things outside the shear zone, the fault. Or maybe if the fault is maybe steep or with a normal sense of shear or normal movement or thrust movement, you can use the thermochronology with apatite to detect the time of exhumation of one of the two blocks if it is different, or usage of morphology to detect the displacement of terraces, fluvial terraces. But from scene sections, no possibility. It's brittle deformation. Okay. When we are in the upper part of the crust, the brittle deformation mechanism are mainly two. Granular flow, the first one on the right. There is a rotation of grains. So like a sand, when you deform a sand, the grain rotate but not deform or are broken. And the second one is a cataclystic flow. There is a fracturing of the formation, a small rotation, but the rock deformed by this kind of fracture that is named cataclystic flow. And it is very common for the formation at the upper structural level on consolidated sediments and the very low grade metamorphic rocks with low porosity. It involves fracturing of crust, development of a matrix, and a very small rotation among grains. Okay. Um, in the upper part of the crust, it is common to find the so-called deformation bands that are bands where deformation is a bit concentrated. These deformation bands are controlled by the mineralogy of the rock, the grain size, grain shape, grain sorting, degrees compaction, rock porosity, and they are more or less tabular discontinuities commonly found in highly porous rocks and sediments, so in the very upper part of the crust. You can see here a thin section of a deformation band in a porous, maybe sandstone or similar. The picture is from Fossen, from the book of Fossen. Okay. So you can have what are so-called disaggregation bands, where you can have in this picture rotation of grains, grain sliding, breakage of the cement binding the grains. Or you can have phyllosilicate bands, the presence of phyllosilicate up to 10 or 15% are reoriented along the fault plane and facilitate the slip movement because they can easily slip along the basal plane of the micas. And okay, this is another kind of band with a large amount of phyllosilicate, sorry. Then we can have cataclastic bands, significant grain breakage with the size of fractured grains becoming much smaller towards the core of the band, which is very similar to the fault and fault core. And you can have also dissolution and cementation bands. You can have the processes of dissolution and cementation of grains. These are more or less the deformation bands that we can find in the upper part of the crust. Okay, at low temperature, there is also another mechanism that is very active, especially in limestone or quartzite, is a pressure solution mechanism. Um, it is active in the presence of fluid because you need to have a dissolution along planes that are perpendicular to sigma 1, to the main stress. This is main stress is vertical. You have dissolution along a horizontal plane. And you have features like these dark themes. In this case, they interrupt these calcite veins. And they are formed because there is a dissolution, some fluid migrates, and non-soluble minerals remain to make the dark matter in the plane. Maybe oxides or some minerals that doesn't go in the fluid, and the fluid migrate and maybe deposit some minerals in the opening fracture like this. Um, Okay, at the micro scale, we can observe truncated grains, sutured grains, boundaries, stylolytic joints, and accumulation of insoluble materials that are these dark grains. In this picture, this movie from Pasquier, we can see the process of dissolution, the contact of grains. There is much more dissolution, truncation of grains. The material from this part move in another ways and it has been attracted by the voids of the opening of fractures. Okay. Here's some evidence of dissolution appearing in deformed rocks. You can see in this section pyrite with some quartz fringe. This, they testify a dissolution, a deposit of quartz in these low-grade metamorphic rocks. And sometimes the fringe are curved because there is a rotation of the pyrite of the minerals during the deformation. There are strong minerals that protect these areas from stress. And in this way, in these low pressure areas, fluid are um, coming to deposit quartz or other minerals. Other evidence of dissolution. Mm. You can have um, new recrystallized grain boundary in optical continuity with other grains, like in this picture, and some trails of fluid inclusion like this that cross the crystal. So when you use a microscope, you can go under big enlargement and you can see some small impurities that are usually fluid inclusion that contain gas or microcrystals, and they testified the occurrence of fluid entrapped during the growth of the crystal. And you can study the composition of this fluid, maybe also the age, depend on the size of the minerals, and they are very useful to detect the kind of fluid operating during the formation. Okay. The evidence of pressure solution are truncated object or mineral zoning, indented boundaries, stylolites, enriched layers with insoluble materials, such as micas, opaque, and precipitation from solution, new grains of a group of grains, and the fibrous vein fields. In this picture, you can see two sandstone grain, two quartz grain that are okay that underwent dissolution along this boundary. And in this case, you can see, okay, pyrite with fibers of quartz with a strong rotation. You can see the direction of the fibers change a lot from here to here. This means that uh, the growth of the fibers happened during the rotation of the main axis of the trail ellipsoid from this position to this position. So, so they indicate also a non-coaxial deformation, and sometimes they can be used as kinematic indicators. You you have only to know if the deformation start from here or from here, because if it start from here, you can initial position like this, then rotation in this position. If the deformation start here, you have the opposite. So you have to check carefully the kind of growth of these quartz fibers. In this thin section, it is low-grade uh, meta sandstone, meta siltstone with um, bigger quartz grains. You can see some dark seams here, and this grain of quartz is has a more or less flat part here against the dark side. Also here, this truncation of these crystals here. This came from the Tibetan sedimentary sequence in Tibet. So there is no deformation of this crystal of quartz. You can see the extinction is totally white or black or gray with no umbrellus extinction, so no deformation, with no ductile deformation. The only way of deformation is by pressure solution. You have shortening in this direction and extension in this one. During the perpendicular to the shortening, you have the development of the um, dark planes of insoluble materials. Okay. Okay, in this fossiliferous limestone, maybe from Malezoc of Sardinia, but I don't remember very well. You can see with the one polars is dark matter with no materials that go in solution. This kind of fossil has been dissolved by compression. It is a good evidence that there was a compression. If you know uh, the total shape of the fossil, you can estimate also the amount of dissolution along this plane. Okay. When we go in depth in ductile deformation, we have to deform the lattice of the crystals that usually they deform by point, linear, or planar defects because perfect crystal do not deform or very hard to deform. But if they are some defect, point, lines, or plane, they accommodate much more easily deformation. In this picture from transmission electronic microscope, you can see the size 1 micron. You can see the surface of um, of a crystal of quartz with these lines that are defect observed by the electronic transmission microscope. Under the optical microscope, you cannot observe this kind of deformation because the solution is quite different. But, for example, in this crystal of quartz, if you rotate the plate of a microscope, the platform of the microscope, you can observe the extinction rotate in the crystal, and this means that the quartz has been stressed and the lattice of the quartz has been deformed. So you cannot observe the single linear or planar deformation, but the total effect of deformation that make a distortion of the quartz lattice, of the mineral lattice. Okay. Okay, these are dislocation observed in steel because a good had been studied a lot by engineers for because deformation or defect are very important for stability of the structure. So they studied since many years ago this kind of deformation. And then we applied it to the rocks the same concept, the same observation, but it is the same in the steel of the minerals are not so much different. So the steel is much more easy to be studied because it is made by uh, one chemical composition, one structure. The rocks are much more different and complicated because you have different minerals. Okay, this is the same as before. Okay, what are the types of lattice defects? There are several kind of defects. There are vacancies like this in a lattice. There is lacking something lacking here. You can see also the picture on the right if the parking is much more easy to understand. There are some extra atom, interstitial atom by missing atom vacancy, the presence of impurity, positions in different sites within the crystal lattice. So you can avoid another kind of atom not observed, interstitial atom, some other kind of impurity. So all these impurity are very important to accommodate ductile deformation. The linear defect are called also dislocation. They are caused by the presence of an extra half plane of atoms within the lattice crystal, such as this one. This is an extra half plane that causes a distortion of the plane. Okay, this is a linear defect. There is some linear defect with a screw deformation with a movement parallel to the plane. You can see this nice picture from Davis. You can see the plane and the screw deformation parallel to the surface, also explained in this part. So edge dislocation, the dislocation plane is perpendicular to the direction of movement. In the screw dislocation, the dislocation plane is parallel to the direction of movement, more or less. And in this way, when you have a lattice with an extra half plane planar deformation, you can move this deformation through the crystal. At the end, you can change the shape of the crystal. It's just one plane, but there are, of course billions of defects in the crystal. So at the end, when you apply stress for a certain time, the crystal should be deformed. These are some picture from Pasquier showing the movement of this defect to the right and the change of the shape of the. This exactly the same. Okay, when you have a slip plane plus a slip direction, you have a slip system. And each crystal have several slip systems that are active depending on the temperature. Because if the quartz, for example, is deformed at 300 degrees, there are certain slip plane or slip system active. If the formation increase, temperature increase, there are other slip systems that are active to deform the crystal. And okay, if it is easy to move the dislocation plane, you have a dislocation glide. If there is some impurity and the plane cannot continue but climb in another lattice position, you have the so-called dislocation climb. That is need much more energy to deform the crystal. These two processes, one plus two, make this the so-called dislocation creep. So dislocation glide, dislocation climb make dislocation creep. There is also the migration of point defect in the grain. So grain scale diffusive mass transfer, high temperature, high fluids, make possible the deformation by movement of pointed effects. This is called diffusion creep. Okay, there is a mass transfer, movement of mass. Okay, dislocation. If we speak about the dislocation propagation, dislocation glide and climb, made dislocation clip, linear defect, diffusion creep. Just as definition. Oh, okay. Is not so important. We can go ahead. Okay, this is a picture of deformation lamelle in quartz. You have seen before ondulous extinction, but when quartz start to be deformed at a lower temperature, you can observe this kind of stripe in the crystal. They're not impurities or caused by the evaporation of the insection of the crushing, but they are effect of the deformation in the lattice of quartz. They are small and thin line across the crystal. Okay, they are active at a lower temperature of deformation. Okay, this is what we call this location climb. I explained before. Um, the slip plane could move in the direction when there is an impurity. It is too hard to go ahead, and the deformation climb in another lattice plane. It need a lot of energy, but it's important to continue the formation and to have a dislocation creep through the crystal. Okay. So when you have a lot of intracrystalline deformation, you can develop a lattice preferred orientation. Uh, since this location move along specific crystallographic planes and direction, the crystal acquired a preferred orientation. You can see here thin section with gypsum plate, and you can observe more or less the same color as I suggested yesterday. That means that the lattice has been deformed, but more or less these crystals have not exactly the same orientation. The z-axis, of course, are not really parallel, but they have a preferred orientation. So statistically oriented in one direction. And you can see the different blue color means that they are more or less oriented in the same way. This is easy to observe in thin section and justify intracrystalline deformation. Okay, so the deformation is caused by the movement of slip system that are the engine of deformation. But sometimes when these locations are locked or there are intersection between several kind of dislocation and dislocation are locked, the crystal cannot deform, no longer deformed, and it is not Thanks. No longer able to move. And this is the phenomenon that is called strain hardening. This means that you need much more stress to continue to deform the rocks. And in the diagram, stress strain, you have the elastic line, then the perfect plastic deformation. And if the line going this way, you have strain hardening, increasing strain to increase deformation. This is due to the mm, locking of dislocation in ivory crystals. So if you continue with the same stress, the rock do not deform, or migration deform towards crystal not yet deformed. Maybe in a shear zone, if you are in the inner part, and there is a lot of deformation, and the dislocation are locked, you with the same stress you cannot deform in the same zone, but you can move the formation in the wall rocks that are non-deformed, so the formation are more easily to happen because the lip system are not yet locked. So, okay, the other way of information is the diffusion creep, the motion of point defect. We have two kind of diffusion creep, the so-called Nabarro herring and cobble creep. I go very quickly. Um, the cobble creep is the diffusion of vacancies along the grain boundaries. So not inside the crystal, but along the boundaries. And what has been called Nabarro herring, Nabarro creep, is the diffusion of vacancies of single atoms through the whole lattice. It's a volume diffusion. So maybe all together are active. And in this nice movie from Pasquier, you can see some point defect that allow the shortening of the in horizontal direction and elongation in vertical direction by moving the single point defect. Okay, this kind of diffusion creep is very efficient at high temperature when the grain size is very small. And when this mechanism is very efficient, we can speak about superplasticity, maybe an increase of deformation due to the small size of the crystal and the diffusion clip, and also by the presence of intergranular fluid film. And generally, diffusion creep is associated with a very uh, lacking of lattice preferred orientation, very small deformation or lacking of preferred orientation. So when this mechanism is very efficient, you cannot see, for example, the quartz with undulous extinction, but the quartz are with a small grain size, but free of a visible deformation. Okay, okay, go towards deformation. Uh, Another mechanism of deformation that is active more or less in more brittle condition is mechanical twinning. Um, that could be active especially in calcite crystal. And you need, for example, in this picture, you have the lattice maybe of calcite, you have some simple shear, left simple shear, and there is some plane of twinnings, and a part of the lattice has been distorted along this plane. And twinning is very well observable in section. You can see different part of the crystal with different orientation. And um, for example, you know that there are mechanical twinnings that are caused by deformation, like the one I am speaking about, and some growth or crystallization twins in minerals. For example, in this picture, you can see crystallization twins in feldspar. The twin planes are very long and continuous, whereas mechanical twins has a tapering shape. So they start here and end here, and whereas the crystallization twins are all across the crystal and are very continuous with no tapering shape. This the most more important observation. In this picture, you can see deformation twins in feldspar because they show a tapered shape. This is much more better because you can see that the twins uh, end in this part of the crystal and then does not continue in this one. So they are caused by deformation in something brittle ductile transition. So it is a way of deformation not completely brittle, but not ductile. And are most are very useful deformation twinings in calcite because they show different shape that that change according the temperature. There is this nice classification by Ferril in 2004. He studied the deformation in the Switzerland alpine nappe, and he checked the deformation by geothermometers, and he observed that according to the temperature, there are different kind of twinings. For example, the type 1 on the left, there are very thin twins, and they are active at a temperature below 200 degrees. The type 2 twins are tabular and more thick twins, and they are active in between 200 and 300 degrees of temperature. The type 3 are curved, tapered, and ellipsoid thick twins, and they are active at a temperature larger than 200 degrees. And the last one, the type 4, they are thicky, patchy twins modified by dynamic recrystallization. They are unstable and they tend to be recrystallized, so they have this corroded shape, this one. And these twins are active above 250 degrees centigrade of temperature. So um, giving a look to the kind of twinning, you can estimate more or less the range of deformation of the rock. Okay, this is more or less the same description. I will left in the PDF. Okay, this is a nice picture from Vernon, the book of Vernon with microstructure. And you can see it is a thick race of twins, a little bit corroded. So they are the type 4, the one active above 250 degrees. So you can assess more or less the temperature of the formation uh, by this kind of gemination, the twinnings, sorry. These are two pictures from Montomoli and others of 2018. They came from maybe the South Tibetan detachment. You can see the type 4 twinings in the upper right picture, and this one may be the type 2 between 200 and 300 degrees. So in this picture, you can see also that the calcite crystal like these or like these are deformed. They show ondulous extinction, and after they have been affected by twinnings. So maybe a history of ductile deformation, then brittle deformation overprinted on this ductile one. Another way to deform minerals such as micas or tabular crystal is a kinking, is a very brittle kind of deformation because you can see in the picture you have a mineral with very well developed basal cleavage. If you deform in this way, compressing in this way, you can start to fold and you develop the kink bands in the crystal, such as you can see in this crystal of kyanite deformed in the Variscan basement. It's a long crystal with the cleavage and is the kink showing different extinction along this plane, more or less perpendicular to the cleavage of the crystal. Okay, so when we apply a stress to a rock, there is an increase in dislocation density. So the more you stress, the more the dislocation density increase in the rocks. So increase the internal energy and increase its instability. And there are several processes which help to decrease the internal energy of the system, trying to reduce the dislocation density. These processes are recovery or dynamic recrystallization, because this situation is not stable, and the system try to decrease the energy to be stable, and the processes through which the rocks mm, come back to a stable position is a recovery process and the dynamic recrystallization. Okay. So the recovery mm, is a mechanism that tends to reduce the dislocation present in the crystal in order to decrease the system free energy. Okay? In this way, when dislocation tend to cluster along planar networks that form the subgrain wall, which divide a crystal into many smaller subcrystal, characterized by slight different crystallographic orientation. The myelonites are characterized by the decreasing of grain size. This is one way to decrease the grain size, forming a subgrain from one big grain, because the dislocation tend to align to go towards some plane in the crystal. And when you form this subgrain, they have a different orientation with respect to the big original crystal, and you can observe in thin section ondulous extinction. And the boundary, that is the subgrain wall, is a plane that separates two fragments of the crystal that have undergone a slight rotation relative to each other. This movement of dislocation tend to align along a plane. So you have a subgrain like this that has a small disorientation with respect to original crystal. We speak about a subgrain if the disorientation is less than 10 degrees, and the new grain if the disorientation is larger than 10 degrees. This simple movie by Pascal, you can see a presentation of the dislocation that try to move toward a wall, and this wall causes the rotation of the subgrains or the grains if the dislocation, if the rotation is larger than 10 degrees. Okay. This quartz with two subgrain. You can see there is a little bit different gray. That means a small disorientation between the grains. When you rotate the plate of the microscope, if the rotation is larger than 10 degrees, you have a new grain. If the rotation is more than 10 degrees, you are in also still in the subgrain. Okay. Mm. In this picture, you can see very beautiful subgrain wall. So the big crystal, that is this one, has been divided by subgrain wall in different subgrain with different extinction angle, highlighted by different gray scale. So this grain has been affected by deformation, and deformation causes the formation of subgrain and later new grain with a smaller size. Okay, another way to minimize the system energy and to reduce the number of dislocation, there is the process of grain boundary mobility, dynamic recrystallization of crystals. That is very important because we can observe very well in section. And this process is related to the diffusion of atoms, of group of atoms from one crystal to another one. For example, in the picture in the lower part, you can see a crystal A with low density of dislocation, a crystal B with high density of dislocation. It is the boundary between the crystal, and during dynamic recrystallization, this boundary tends to move from the lower density crystal towards the high density crystal. So the boundary between the crystal is not stable, but there is movement, so changes the shape of the boundary in this way. And the main mechanism that drive the crystallization of new grains to reduce dislocation are the bulging, subgrain rotation, the grain boundary migration. Do you remember the first picture I have shown? Too many slides. Okay, this picture, you can see different temperature, different names, and the mechanism of the formation of quartz that are bulging, subgrain, ground boundary migration, active with increasing temperature. So we will give a look to these mechanisms that are quite well observable under thin section. Okay. So we start with the bulging. So there are mechanisms that allow dynamic recrystallization of quartz. Okay, this is a quite common fabric in quartz, especially at a lower temperature. And dislocation are accumulated towards the crystal that has a higher dislocation density, as we saw in the slide before. And there is a migration of the boundary. So the typical structure is core and mantle structure. You have a big crystal with some small crystal along the boundary. Because here you have the mobility of the boundaries that you can see here. There is mobility from this crystal to the other one, here, here. So the boundary are moving. You have not more the straight boundary of quartz that are lines, but are um, very the shape like this. Okay. So the grain distribution is bimodal. You have larger grains and smaller grains, two grain size. Is a bulging. Is a picture from Fossen maybe with a strained grain, less strain on the left. The boundary tend bulge in the high strain grain, then form a new grain. After the bulge, this part creates a new grain. So from a big grain, you create a lot of new grain along the boundary due to the different intensity of dislocation and the bulge in the direction of the high density crystal. This is an example of a bulging in quartz. Are also this line deformation lamelle, and the bulging are big crystal and the new crystal along the bound. A modal distribution of the grain size and the accumulation of new grains along the boundary. It is called also mortar structure. Someplace. Okay, is the same process, little bit gone ahead in the Barbagia Trust, the Bariscan basement of Sardinia. We are in very low-grade metamorphic condition, green schist. Usually you have no more than crystallization of quartz or chlorite. Is a big amount of quartzite along this trust, and the only observation that became made is the formation of new grains, small new grains, after big grains by this mechanism of bulging. obviously, after a lot of time, the new grains increases and the older grains become smaller and smaller, are reduced by this process. Okay, this is the same. Increasing in temperature, we have another more efficient mechanism of deformation that is called the subgrain rotation mechanism. It's very similar to the previous one, but as you can see in this picture, you have a subgrain like this, but this grain rotate and form a completely new grain. So there is no other movement of the boundary of the crystal, but only rotation of the subgrain to create a new grain. So the subgrain are also present in the rock by previous mechanism, and the rotation causes the formation of new grain. And with time and deformation, the new grain can completely replace the original crystal. So the original big crystal are lost, and we have a lot of new grain, smaller new grain. Is just a simple picture to show the concept. Okay, in this scene section by Pesquet and Trau, there is a subgrain rotation, is a remnant of the old grain. These are the new grain formed by rotation of subgrain previously formed. So at the end, if the process go ahead, you have only this kind of crystal in the rock, completely and completely the other grain is completely lost. This process go ahead. You can form also subgrain and the new grain, and the grain size reduce continuously. So at the end, continuing with this process, you have a grain size, a stronger grain size reduction, and the very common in the production of myelonites. Is a picture for my former PhD students, Matteo Simonetti, that studies the Argentera Massif, is the big shear zone that we studied, the type 2 shear zone with deformation increases from the boundary to the center from 335 to 310 million years. And also we observed also the deformation. We studied the deformation in quantitative matter with Rick Lowe in the USA. And in this picture, you can see a lot of subgrain and new grain by subgrain rotation. So the big crystal completely disappear, and you have also only new grain and some subgrain. Yeah, and okay, this is a much more nice picture from Akonfossen. On the grain, subgrain with small different orientation with respect to the other grain, and here the formation of new grain of the same size but strong different orientation by rotation of the lattice of these grains. So at the end, from one big crystal, you have 100 of smaller crystal. The process of grain size reduction by dynamic recrystallization with no fractures, but only ductile deformation. Increasing the temperature, the mechanism active to deform the rocks is a grain boundary migration. It occurs at a higher temperature with significant increase in grain boundary mobility. So this means that these boundaries that are moderate, straight, a little bit curved, became more and more sinuous, amoeboid, with a strong mobility. So grain boundaries are lobated or amoeboid in shape, and the original grains are very difficult to recognize. There are some characteristics that help to recognize this mechanism. So the first one is the shape of the boundary, of course, and the other one, the window grain and the dragging microstructure. I show you what I means. This is an experiment by Winthrop Means, one of the geologists that studies a lot the formation of the rocks in the 80s and the 70s. This is an experiment in analog material, and you can see the recrystallization by ground boundary migration. So the starting point is from crystal of something similar to quartz with straight grain boundary, no big problem, but increasing deformation and temperature, you can see the mobility of the grain boundaries. So to the end, you have not many straight boundary like this. Boundary are uh, very ondulous or amoeboid in shape. This is an evidence, the first evidence of grain boundary migration in experiments. At the micro scale, we have some picture of naturally deformed rocks. Again, the Argentera massive, the formation with high temperature. You can see the grain boundary between quartz is made by these very contorted lines. Also here, you can see this kind of lines, or here. Okay, this. Okay, about this kind of evidence, the pinning, window, dragging microstructure, leftover gains, there are typical structure that are active, are visible during the boundary regime. Okay, the pinning is, you can see in this picture, you can see the movement of the boundaries and maybe minerals like this, like a mica, that make this kind of shape that obstaculate the movement of the boundary, like in this part. You can see this mica and the boundary between light gray and dark gray here and here, and this is a typical pinning structure. Dragging microstructure like this, there is a movement of the boundary towards the right, but there is some dragging along this uh, orange crystal that could be mica typically or some other crystal. So this is typical of grain boundary migration. The window microstructure, you have two crystal with a small window inside, and when there is a movement, of course, the movement can happen only in the window, causing this kind of structure. Leftover grain, there is a movement of the yellow crystal towards the red one, and some small part of the red crystal are left along the boundary. The name is leftover grain. Okay, this is some example. Argentera massif, this is the process. Argentera massif, you can see this kind of pinning structure. This is from the Kaligandaki in the part of the Higher Himalayan sequence when we studied the Kalopani shear zone active in the higher part of the Himalaya, nearly 41 up to 30 million years in high temperature condition. And of course, we studied the temperature and pressure by garnet, biotite, staurolite occurring in the rocks. But the deformation of quartz was a grand boundary migration with this kind of pinning structure, confirming more or less the range of temperature detected by PT condition. This picture of the Argentera Massif, the shear zone, Est Variscan shear zone, you can see two mica crystal and the window structure like this. The formation is this, so there is a movement from the light gray into the dark gray across the window because the boundary cannot cross the mica crystal. Okay, after this, there is the recovery or static recrystallization mechanism that continue until the system reaches a minimum energy configuration. In this kind of recrystallization, the crystals tended to increase in size, reducing dislocation density, and there is also grain boundary area reduction. Mm. This could happen in metamorphic rocks, sorry, because you have deformation and temperature. When you are in fabulate phases, maybe at 600 degrees, you can deform the rocks by folding or by shearing, but you can stop the formation because maybe the shearing stop, but the temperature of the rocks remain high, and the transfer of heat from the rock is not so quick. So you can stop the formation, but the rock continue to be hot. And in this way, you can have static recrystallization or, or annealing. So the rocks tend to find a new minimum energy configuration. So what has been done by deformation has been tended to be cancelled by static recrystallization on annealing. And this kind of boundary created by grain boundary migration are unstable, and the grain tend to have a big grain size and an area reduction. So at the end, you can have an evolution from this kind of boundary to this kind and this one. Mm. So at the end, you can have straight grain boundaries, homogeneous grain size with respect to the original, to the deformed rocks, triple junction between grains forming the 120 degrees in crystal of the same phase, for example, quartz, and more or less absence of internal grain deformation, no undulus extinction. So all the deformation tend to be erased, cancelled. Okay, in this movie by Pasquier, you can see the process. And here is the effect at under the thin section. You have a strong deformation history with several deformation, shearing, and so on. But when deformation ends and temperature remain high or diminish very slowly, you can have a complete reorganization of the fabric. So in a quartz domain, you can have polygonal quartz grains with no undulus extinction, so rocks appear not deformed. It is a pity for such archaeologists because you lose the previous information about the formation. You can see uh, similar phenomenon in olivine, albite, scapolite, orthopyroxene, and plagioclase. These are deformed rocks, but underwent thick recrystallization. This is an analog experiment, maybe, I don't know, from Pasquier. Yeah, so also under experiment, this kind of recrystallization has been reproduced. So at the end, you have bigger grains with straight boundaries and no more traces of deformation. Okay, this is another experiment. Okay, now I will show you this paper, more or less the main result by this paper by Michael Stipp, Holger Stunis, René Bronner, Stefan Smith, that studied the tonale fault zone, that is a big shear zone with an intrusion of the Damello granite. And in this way, Michael Stipp, during the PhD work thesis, studied the intrusion of the tonal intrusion. You can see here the temperature of the contact metamorphism, 620, 570, 400 degrees. And they studied also the deformation of quartz because there is an increase in temperature from the granite towards part away from the granite. But since there is the tonale line, that is a big shear zone, the intrusion is contemporaneous to the formation. So it is a unique opportunity, was a unique opportunity to study the deformation during increasing temperature in a system not so complicated with intrusion and deformation. And in this study, they first demonstrated that bulging was active in this area, like this picture. You can see core mantle structure, small crystals along the grain boundary. So we are in the lower temperature zone. The subgrain rotation recrystallization in this part. So with rotation of subgrains giving rise to new grains. And in the higher temperature portion, above 570 degrees, grain boundary migration up to the boundary to the tonale granite with amoeboid contact like this, and chessboard extension on quartz. There is a extension with a square like a chess board. Okay. Was a very nice paper because after that, this kind of microstructure was applied to infer the temperature of deformation in regional deformation. Uh, Now, um, Stipp is not so convinced of this work. We had a workshop last year in Kharagpur, and Michael Stipp was present, and he worked. He made a lot of experiments, and he didn't confirm the more these first results. But some people, there was a big discussion because other people, because of course it is not so simple, but there are other factors affecting the, diciamo, deformation because the fluids, the strain rate, they change a little bit the situation. But anyway, if you have this kind of microstructure and some other constraint, you are quite confident to apply this one. So uh, we are not so destructive like Stip in this last year. Diciamo, when we observe this deformation mechanism, when we applied ETT deformation and so on, there is a good agreement in between several observation. This is quite important. Just okay, you cannot say 355 degrees. You can have a large idea of the formation, but sometimes it is important, especially in sequences where there are a lot of quartzite or a lot of marbles, no more minerals. So at least we have an idea of the range of the formation. Okay, in this graph, you can see the distance from the Pluton margin in meters, 0, 1000 meters, and here the temperature. And you can see far away from the Pluton at a lower temperature. Here there is a frictional viscous transition just below 300 degrees. Then bulging is active. Here, nearly at 400 degrees, there is a bulging subgrain rotation transition. This is subgrain rotation, grain boundary migration transition, subgrain rotation, grain boundary migration. You can see also they check also the occurrence of minerals to detect the temperature. Chlorite plus K-feldspar, muscovite plus biotite, cordierite plus andalusite, K-feldspar plus sillimanite. So there is also a constraint after petrology on this kind of temperature and transition from the Pluton towards the external part of the contact metamorphism. Is more or less okay. They also estimated the grain size that is related to temperature. in the paper STIP 2002. Increase in temperature, there is an increase in grain size. This seems to be normal, but it was first demonstrated by this paper by STIP. So you have logarithm of recrystallized grain size, micron, and here the temperature. And you can see that increase in temperature, the change of course the mechanism of deformation, but also the grain size. So in this case, approaching the Pluton, increase in temperature, there is also an increase in grain size during millionitic deformation. So it is not always true that the deformation causes a decrease in grain size. It depends also on the temperature. If temperature is very high, there is an increase in grain size. This has been demonstrated here in the Tonale fault and also in the Bergel Pluton, the Bregaglia Pluton, by another geologist, Italian geologist who works in Germany. I do not know the name, I forgot, unfortunately. But it has been observed very clearly in the Bergel Pluton because you can observe a strange shape of the Pluton. It is quite circular, then it is elongated along the shear zone, like the Manaslu Pluton in the Himalayas. So there is an increase in deformation approaching the shear zone, and also in this case, they observe the big grain size increase along with deformation. Okay. So in this, there is a nice paper by Richard Law that works a lot of in the Himalayas. Probably you know his name. It made a nice review of deformation mechanism in quartz in 2014 in the Journal of Structural Geology uh, journal. It is a very big paper, but very nice. Here it show increase in temperature and also the amount of water because the presence of fluid affects the deformation mechanism. And here you have also the strain rate because this is also a factor affecting the crystallization of quartz. So at lower temperature, lower presence of water, lower high strain rate, you can have bulging, the bulging mechanism that we described before is all the grain deformed by deformation lamelle, kinking, very few new grain, and the core and mantle structure. In the subgrain rotation, the middle part is increasing temperature and increasing presence of water and decreasing strain rate. You have a subgrain rotation that is made by old grain with subgrain, and deformation bands. New grain is a size similar to the one of subgrains. Bimodal distribution of grain size, core and mantle structure, but all the grains can be totally substituted or erased by new grain and subgrain. The grain boundary migration, you have high temperature, high amount of water, low strain rate. You can have all the new grains difficult to recognize, of course, because of total recrystallization. Amoeboidal grain boundaries, I showed before. Unimodal seriated grain size and strain-free grains at a high energy. So the problem is that this mechanism has been described mainly by temperature, but also the amount of water is thinking to affect deformation and also the strain rate. So uh, high strain rate, you can produce bulging deformation or low amount of water. So the, the range of temperatures could change a little bit. Okay, this is an experiment shown by Law in the review paper. You can see here experiment with dry in dry condition. You can see regime 1, regime 2 of quartz, regime 3, you have deformation temperature and the strain rate. There is a configuration of this regime of deformation that are more or less the same or combination of these. If you add 0.17% of water, you can observe a shift of these three regime towards the lower part of the graph. So there is the amount of water and the strain rate affect the temperature at which you can observe bulging, subgrain, or grain boundary. So it is true these processes affect the formation and the structure. So you can only a general idea of the temperature, but you can follow the temperature. Okay, regime 3 is combined grain boundary migration and the progressive subgrain rotation. That is regime 2, progressive strain subgrain rotation crystallization. And the regime 1, grain boundary bulging recrystallization, more the same. But there is a shift of these three regimes according to the amount of water or the strain rate. Okay. These are more or less bulging recrystallization. Sometimes people recognize two types of bulging 1 and bulging 2, but it is not easy to recognize in section unless you study all your life the formation mechanism of quartz. In bulging 1, recrystallization occurs at the triple junction of the crystal. Some fractures could be present, and the volume of crystallized grains is very small. You start the formation at a low temperature in this case. In bulging 2, the formation increases with temperature, and no fracture or very few fracture. Ondulus esteem formation lamelle in quartz grains. Crystals are elongate. Crystallization is and develops a core and mantle structure, as you can see here. So there is an increase in deformation, the little increase in temperature. This paper is again from Steep and other 2002. With a subgrain rotation crystallization, this is a picture I showed you before. You can see the deformation is no longer concentrated along grain boundaries, but go inside the old crystal. And sometimes the porphyroclasts, the older big grain, are completely recrystallized and disappear. In grain boundary migration, you can have pinning, window, drudging structure, and so on. But pinning structure are present at the beginning of and are absent in boundary migration, the second stage of increased temperature, according to the paper by Steep and others. Okay, this picture is an evidence of a chessboard extinction in quartz. This a quartz crystal. You can see the square. So the extinction happened along long square, and it is a characteristic of high temperature in combination with a grain boundary migration, and these indicate a temperature larger than 600 degrees. When you observe this in quartz, you are surely above 600 degrees. This picture came from Nepal, maybe what we call the Mangri shear zone in western Nepal, along the Mugu-Karnali River. We found the shear zone in the middle of Great Alien sequence with a ductile deformation in high temperature condition that we detected by thermobarometry and also by deformation of quartz like this. Is also another shear zone with chessboard extinction, not exactly the same place, but in the continuation towards the southeast. And you can observe here this chessboard extinction of quartz. Okay, now we give a quick look to the deformation mechanism in K-feldspar and pleasure clays. Because we spoke about more or less of quartz that is very common, but also feldspar is common in rocks. So just to have an idea of what kind of formation they could develop. Okay, in a low metamorphic condition, when temperature is below 400 degrees, you can observe in quartz of course brittle deformation, cataclastic flow, maybe grindings, and this is a typical deformation of quartz as we saw yesterday. So quartz recrystallized in dynamic way, and the first part is fractured with a high angle fracture with a shear zone, all uh, small angle fracture, but the way is brittle. Okay. With increasing the temperature, the formation between 400 and 500 degrees, the deformation is still a little bit brittle. There are some dislocation glide active and a possible bulging mechanism along the boundary of the plane. Sometimes deformation bands, ondulatory extinction, like in this crystal. There are no core structure, or you can observe flame pertite or bookshelf structure, but anyway, deformation of the lattice and ondulatory extinction. Okay, this is a picture you know from yesterday. Okay. Moving to medium gradient metamorphic condition after 500 degrees and below 600 degrees. Bulging is a dominant mechanism. Possible some dislocation climb as a mechanism of deformation of the lattice. Recrystallization becomes very important. There are a lot of core and mantle structure, abundant flame pertite, and the mimikites start to develop in high stress zone, such as this boundary of the crystal. You can observe plagioclase quartz with cauliflower structure in the areas subjected to high stress. After 600 degrees, after bulging, there is also submarine rotation, and these two mechanisms are dominant. Location is active, some recovery. Core and mantle are developed with less defined boundary between core and mantles, abundant myrmekite, non-flame pertite. After physical temperature above 850 degrees, subgrain and bulging grain boundary migration with the production of because under this temperature condition, much crustal rocks are molten or become to, to melt. There are three strain-free grains, myrmekite, interlobated grain boundaries by grain boundary migration, and a lot of leftover grain. So this is a summary of the characteristics of deformation observed in plesioclase feldspar with increasing temperature below 400 500, 600, and so on, what I mentioned before. So you have a reference also of the deformation of feldspar in rock. Okay, this is just a picture. Is high temperature deformation. There are some quartz ribbon maintained as a shape, but with a strong recrystallization inside. You cannot observe uh, mm, oblique foliation, but there is a complete crystallization with a crystal with a strong, with a strange shape due to crystallization and of ribbons. And of course, the metric is granoblastic because it is completely reorganized by recovery or crystallization due to high temperature. So when you observe a rock like this, you can imagine a peak formation because there are some ghosts of this ribbon quartz, but the structure is completely destroyed. Okay, I can stop with this long excursus on deformation mechanism. So this afternoon, after lunch, we can talk about foliation and porphyroclast for at least 1 hour and a half. When we move to the geological department to observe some scene section, to classify foliation and to detect the occurrence of porphyroblast and the relation between porphyroclast and foliations that are very useful to reveal the deformation history of metamorphic rock. Have you some question about this part? It's a little bit complex because there are a lot of deformation inside the crystal lattice which are not so familiar usually these kind of things, but we gain the results from the people found of this and we try to use for the deformation of the rock. Anyway, in the book of Pasquier, there is a lot of information about this. And I also suggest to read the paper by Stefan Smith if you are interested in go into depth of this topic. Hmm. But what is the temperature of the thermal system in the higher temperature? 200, 100, 9400. Surely you can observe some alteration of the rocks around. No, no, not much. But there is deformation associated with this geothermal system, some fault or no, yeah, a lot of. Oh, there are a lot of hot springs along the MCT. Okay, you can try to observe some fracture close to the hot spring, and then to observe the mineral growing in the fracture, maybe alteration minerals. Quartz. Ah, oh. This kind of deformation is difficult because you can start to observe deformation after 200, 300 degrees. So you need much more higher temperature. Mm. Mm. Okay, if the hot spring started in older time when the formation was the tile, you mean? No, no. Mhm. But the deform Mhm. Mhm. Okay. Mhm. Yeah, 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 of course. Mhm. Oh, yes, yes. Mhm. Mhm. Yeah, yeah. Yeah, because main central trust started to be active several million years ago with in ductile condition. In the main central trust zone, there is sorolite, kyanite, garnet, an inverted metamorphic sequence. So the temperature was and the pressure was a little bit higher. Uh, um, but probably the occurrence of hot springs along the main central thrust could be to later faults, not really to the ductile deformation, because it is too old. Probably, yeah. Mm. Uh, you served a lot of hot springs in Uttarakhand, also in Nepal. Yeah, yeah, yeah. But it is difficult to see a relation with the tile deformation and hot spring because um, probably when the rocks comes to the surface, they are too cold, and probably this system is activated by other fault that allows the water to go into depth, to warm and come up again, probably. But we have to check the occurrence of fault or important fault. Mm. It is interesting. Uh, Also, the nature of the fluid coming out from the water, uh, relation with earthquake. After the Gorka earthquake in 2015, people observed different compositions of fluid coming out from the hot spring south of Manaslu because there was a group checking the composition of the fluid just before and after the earthquake, and they found the difference. So it could be very nice also to. Mhm. Yeah, yeah. Mhm. Oh, so thanks. They're nice also to swim in the hot spring. And, uh, after the trekking to check rocks to collect rocks, when we found hot spring, we go in the hot water. It's very nice also for this. Okay. Thank you. Enjoy the lunch. And also we will observe some deformation mechanism in scene section this afternoon. Hmm? Ah, okay. Ah, mhm. Yeah, yeah. Well, the Drello is just in Tuscany, in the central part of Italy, and the crust is extended by the calc extension due to the retreat of the of the Adrian slab that is retreating, opening the back arc, and the mantle in Larderello is just 3 kilometers below the surface. So yeah, there is a high heat flow, a lot of hot spring and vapor utilized since the early 90s to produce energy to to warm the houses. It's nice. Yeah. We need some theoretical lesson before, just porphyroblast infoliation, 1 hour, 1 hour and a half. Yeah, and then we move. Okay. 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 So we will now speak about the topic of foliations in the rocks with some practical observation. And in this lecture, I will explain you what is the foliation, how to describe and classify a foliation. Just give a look to the mechanism of foliation development, but only few slides, and the recognizement of foliation and their relation with the tectonic processes. Okay, a foliation is a general term that we use to describe any planar feature that occurs penetratively in a body rock. We can distinguish primary foliation, diagenetic foliation, and secondary foliation. The primary foliation is very easy, you know very well, because, for example, primary foliation is the sedimentary bedding in the rocks, or the magmatic foliation in magmatic rocks when they in place in the country, when the magma in place in the country rocks. So you have several characteristics to distinguish primary foliation, such as crossed or parallel bedding, variation in layer thickness, grain size. So the features that you know very well. But the most important thing is that primary foliation and has no genetic and geometric relation with folds. You can have a foliation related to the fold only for tectonic foliation. Okay, these are two examples, one from the island Elba in Italy. There is a huge granite, granodiorite, with the development of a big K-feldspar crystals that show a preferred orientation that is caused by the emplacement of the main body of the granite in the country rock. Here on the left, there is a granite that we found in western Nepal, Buraburi granite, dated 45 million years, 44 million years, sorry, 24 million years. And we can observe here alignment of muscovite showing a preferred orientation, but with no deformation inside the feldspar, quartz. So this alignment was obtained during the flow of the magma during the emplacement in the greater Himalayan sequence. So these are two examples of primary foliation in magmatic rocks, not due to tectonic processes. Of course, if you speak with Manish Mamtani, that is a structural geologist from Kharagpur, he studies the deformation of granites. He says that this magmatic foliation is due to the overall field of stress. This is true, but it is not, strictly speaking, a tectonic foliation. There is, of course, a stress along with the emplacement of the granite, but the foliation is not of this type. Another kind of foliation that you can find in sedimentary rocks, especially in pelitic rocks enriched with mica, is diagenetic foliation. They are planar anisotropies developing during the rock during the diagenetic processes. This kind of foliation is very well observable in very low grade to low grade metamorphic rocks. After that, disappear because metamorphism makes them much more important, and we have recrystallization. So the original digital grains usually disappear. This should be very dangerous when study deformation in very low grade metamorphism, because the compaction of the sediments give rise to alignment of fragment of white micas and so on. So you have a foliation parallel to the bedding, but it is not a tectonic foliation due to the deformation processes or folding processes, only by the compaction of rock, like this. Maybe after that you can have deformation So diagenetic foliation is formed like this due to the decrease of volume of the sediments. After that, you can have deformation with a shortening, formation of fold, and effoliation, uh, axial plane of this fold. And sometimes when the spacing of the diagenetic foliation, the tonic foliation is of the same kind, you can develop the pencil structure. It is long prism of of sediments deformed by these two orthogonal foliation. Okay, so when working with very low-grade metamorphic rocks, mm, sometimes the diagenetic foliation look like a true tectonic foliation. So be careful to distinguish the one. In metamorphic foliation, you have well-developed white micas. In this kind, you have different size of white micas, for example, with some disrupted end of the some not very beautiful crystal, but corroded with flames or so on. So, and the composition is different because micas that grow during a metamorphic condition in PT maybe 200 degrees 3 kilobar, the micas have more or less the same composition. In the triton micas, you have very different composition. So you can check the composition of the fingite contents and so on. They are very different. So there are some ways to distinguish, but we need to be careful. Okay, and the secondary foliation is a tectonic foliation sensu stricto. And in this kind, we we can use this foliation to reconstruct the structural evolution of rocks. Usually foliation are associated to folds. Here you can see a fold, one limb, the hinge, another fold, and an axial plane foliation. A foliation that more or less is statistically parallel to the axial plane of the fold. The other kind of formation of foliation is during shearing the shear zone. This is an example for a shear zone South-Tibetan detachment system, leucogranite. You can see this S and C foliation. This kind of foliation is originated in shear zone. So or shear zone or folds are the two ways to develop foliation. So this is just an example of the axial plane foliation. Is very low grade meta sediments with beautiful bedding like this, folded, and penetrative axial plane foliation, especially developed in micaceous material or argillaceous material. Foliation show develop a selective development due to the lithology. Maybe if you have quartzite or sandstone or pilites, foliation is very well developed in pilites and less well developed in quartzite in much more resistant or viscous material. There is also the phenomenon of foliation or refraction of foliation that, of course, in quartz granite material, it is less developed because the competence is higher viscosity during deformation, and in less in weaker material or material enriched in pelitic layers, it is much more well developed with this shape. This shape is very useful when metamorphic grade increases and you cannot recognize very well the grain size due to recrystallization, but you can see the foliation with this shape and you can say that the top is to the higher part. Sometimes it is useful in increasing metamorphic grade when the sedimentary bedding mm, become less evident as the structure are destroyed by recrystallization. Also, the foliation can be refracted. We are in the Northern Apennines in Italy as meta-cherts and metapilites. In metapilites, the foliation is much more well developed, much more pervasive. When the foliation cross-cut a much more competent bed, rich in quartz and quartzite, the angle of the foliation change a lot. and the angle became close to the normal of the to the foliation. And the foliation is much more spaced in this more competent layer. Okay. Oh, you can use also the relation between the bedding on different limb of the fold because you have a different attitude of the bedding of the foliation in one limb or in another limb, and you can use this relation as well as the S or Z shape of the fold to detect if you are in one limb or in another limb of the fold. Okay, now we try to go towards the description of the and the classification of the foliation. We normally use this classification of the foliation made by Pasquier and Trau in the book. This is a geometric classification, does not imply genetic processes. So we can describe just the geometry of the foliation without giving an interpretation of this. So the first question is, are microlithon present? No. If no microlithons are present, you are in the case of the continuous foliation. So the rock is affected completely by a foliation. Every volume of the rock is affected by foliation with no spaces with no foliation. And the foliation could be fine-grained, depend on the minerals, or coarse-grained, depend on the minerals. If you are in low-grade condition, you can speak about the continuous cleavage or slate cleavage. If a metamorphic grade increases, you have big minerals and the coarse-grained minerals, so you have a continuous schistosity. And the grains are visible also with without a lens or microscope. In the second case, you can move to this part. If you have microlithons, you can speak about spaced foliation. A spaced foliation um, is made by cleavage domain where the cleavage is well developed, alignment of mica, rotation of minerals, and this white stuff is a space in between two cleavage domains where no foliation develops. So you have no foliation here, a foliation here, no foliation. This is a microlithon, and this is a cleavage domain. So you can go to a further classification. Uh, if you can recognize a granulation inside the microlithons, inside this space, if you see microfolds, maybe granulation, you can speak about granulation cleavage. If nothing is visible in between the cleavage domains, you can classify this as just disjunctive foliation. Okay? Because it is a first classification of the foliation. Now we will see some example just to be more confident with this. This is a section of a quartzite with a lot of micas. There is a homogeneous distribution of platiminerals grain, this one, that are micas. The different color is dependent on the thickness of the thin section, because it change a little bit from this part to the other part, but the mineral is the same. So you can observe, you can give a look to the scale, 1 centimeter here. Every volume of the rock is affected by foliation marked by white micas. With not much more deformation in quartz grains in between the one. So this is a continuous foliation. Okay. It is a continuous foliation that is defined by flattened crystal, maybe quartz or calcite. These are calcite crystal here, is a sample from the South Tibetan detachment, the Kaligandaki Valley in marble. In marble, this is also a scene section in calcite. You can note these prints in calcite. The colors are due that the scene section is all maybe 5, 10 microns, no more, because in this way you can observe very well the boundary of calcite that with 20 or 30 micron is not well observable. But in this way, the foliation is this one, and is made by the deformation of flattened crystals of calcite. Okay, it is a continuous foliation. Okay, if the foliation is continuous, you can go ahead and try to classify if there is a continuous cleavage, if it is fine-grained or coarse-grained. The scale of the picture is the same. I use the same scale of the picture. And you can see that you have also flattened crystals, small mica, but all the volume is affected by foliation planes, and the grain size is very small. So this is a fine, continuous foliation. At the same scale, not the 1 centimeter scale, you can observe that the grain is much coarser. You have a bigger quartz crystal, bigger um, white mica crystal. So this foliation is continuous, but coarse, little bit also due to the increase in metamorphic grade, and so the increase in grain size. This is an amphibolite. You can observe amphibole, hornblende, garnet, completely black, plagioclase, and of course, this kind of rock is found in amphibolite facies, metamorphism, and the minerals are quite big, so they are aligned, flattened, part of the garnet that is a little bit more hard to deform at this temperature, and you develop a coarse continuous foliation due to the grain size. Here's another example, similar to the one before. Okay, if we can give a look to the spaced foliation. So you have to detect if there are cleavage domains and microlithons in between two cleavage domains. And after you have detected the occurrence of microlithons, you have to go to look inside the microlithons to look at the structure inside, or nothing, or macrofolds. In this case, you have a disjunctive space foliation because you have here cleavage domains made by maybe amphibole or similar. In the microlithons, you have quartz and feldspar, but not microfolds. So you are in this case spaced disjunctive foliation. Here it's very different from a previous case. You have a space foliation. These are the cleavage domains. This one, this one, this one. The enlargement should be 20, 24, 20, 20 magnification. This sample came from the Tetian sedimentary sequence close to the Kangmara Dome in southern Tibet. There are metaphylites of maybe Triassic age, a little bit metamorphosis close to the metamorphic dome. So you have cleavage domains here, cleavage domain here. Inside the cleavage domain, in the microlithon, you have fold. you have a foliation that is folded. So in this case, you are in this one case, crenulation cleavage. Mm. This means that you are observing at least two deformation phases, two episodes of deformation. The first one is this, giving rise to this foliation, continuous foliation that has been folded and affected by this second foliation that is more or less axial plane of fold like this. So crenulation cleavage are usually found in at least two deformation phases. Mm. And take care because this foliation is the older one, folded, and the new one is this, which is the straight one. Okay, you can go ahead if you like to better this foliation. You can give a look to the shape of the cleavage domains. They could be rough, smooth, wriggly, or stylolytic. It depends just on the job, the shape of this kind of domain. You can also try to calculate the percent of cleavage domains, 10%, 30%, 7%, 100%. Of course, you are increasing deformation in this direction. Also, you can have parallel cleavage domain, anastomosing, or conjugate cleavage domains. So there's another way to classify. Also, in relation cleavage, you have to detect the transition between the cleavage domain and microlithons. Could be gradational or discrete like this. So you can, of course, this a further fine classification that you can use, but it is not always requested. Anyway, we will some case of this classification. If we give a look to the shape of the cleavage domain, this kind of lines, we can describe this as smooth. So the first one here in this case, more or less, this or this. Ah, sorry, this. Uh, Sometimes the difference is not so strong. You can be in between here and here because the deformation is much more complex. Our classification. Okay, these the cleavage domain are rough or are discontinuous, are not perfectly developed, and this is because of the competence contrast between this layer and this one is much more rich in phyllosilicates, is much enriched in quartz, and so the development of cleavage is anyway the shape is rough. Is a good example of stylolytic cleavage because it is spaced. The shape is just of stylolites. You can see the fossil dissolved by the stylolytic cleavage here, here. So this is quite easy to recognize. Also in the field, especially in limestone, is very common in low-grade deformation. You can observe large stylolites, maybe spaced on 1, 2 centimeters, and so on. Okay, just to have or try to estimate the amount of strain, you can joke with the percentage of foliation. So in this case, you can have maybe 30% of cleavage, maybe 20, 30%. But if you are observing a strain gradient approaching maybe a shear zone or a thrust, you can observe an increase in the deformation cleavage plane. So they are increasing, and you can make quantitative estimation approaching the thrust or the shear zone. if you use the spatial relation between cleavage domains, in this case, due to the presence of big minerals and smaller minerals, the shape of this foliation of this cleavage domain is like this anastomosing because they cross more or less in this way. Mm. Also here you have not easy uh, classification, not easy development of foliation, but there are cleavage domains. These are all their foliation with big crystal, maybe garnet, plagioclase, and so the shape of the granulation cleavage is anastomosic-like because of the different size of the crystals. Okay, here very simple uh, movie by Pasquier showing the development of the granulation cleavage. You need a previous foliation formed during tectonic event. Then you make a compression, maybe horizontal compression. Then you fold this foliation. This is the crenulation cleavage, the microlithons with the foliation inside. So very easy. Okay. The last classification is to give a look to the transition between the cleavage domains and the microlithons. If it is sharp or continuous, mm, gradational or continuous. In this case, you can see that the cleavage domain is just developing and the transition is gradational. So there is no interruption the cleavage domains and the fold in the microlithons. Also in this case, there is a gradational passage from the cleavage domains and the microlithons. Oops. In this case, you are in a sharp transition between the cleavage domains and the microlithons. There is no so much continuity, but a strong difference. There is a interruption here, so you are in this case. This is also due to the increase in strain. If you increase the shortening, you go from here to this better development of the transition. And now, if we give a look to the main mechanism of foliation development, of course, there are several factors affecting the development of foliation. The first one is rock composition, of course. Then metamorphic condition, including temperature, static and fluid pressure, the fluid composition, and the stress orientation and magnitude. After that, the foliation can develop by the mechanical rotation, solution transfer, crystal plastic deformation, dynamic recrystallization, and also static recrystallization. All these mechanisms could affect the development of defoliation. You can see in this pre-deformation state and deformed rock. After deformation, you have, for example, these minerals rotate toward parallelism to the uh, elongation lineation or foliation plane and try to, of course, to concentrate here. Also, this isotropic line rotate to mark the defoliation. Crystal plastic deformation means that you have deformation of this crystal with a mechanism described this morning to elongate the mineral, to shorten in this direction. You can have also maybe like pyrite and strain fringe with a solution transfer. you can develop the fringe parallel to the foliation. Uh, so all these mechanisms contribute to development of foliation. This is quite easy. Proceed by Fossen. You can see isotropic orientation of minerals when shortened and elongated. They become parallel and mark the foliation. So that is an active mechanism with abundance of fluid, and you have the presence of one or more soluble minerals. So they, during maybe the folding of the previous foliation, you have a rotation of the minerals that became parallel to the limb of the fold, but could be also some solution transfer, uh, highlighting on emphasizing the development of the foliation. Of course, there are minerals that are more soluble than others, but cite very easily to the oxide are very hard to dissolve by fluid. Crystal plastic deformation means that you flatten this quartz crystal, maybe in low-grade metamorphic condition. They flatten in direction, elongate in this one. They change the shape by movement of dislocation, but without um, Ondelus extinction and so on. So in this case, they are flattened along the first foliation. Then there is another foliation, inclination cleavage. In this case, you can use also this quartz crystal as a strain marker to detect strain because they are not recrystallized, they are not fractured, and they are marking the deformation since the initial stage up to this stage of deformation. So in this case, you can use this to quantify the strain that underwent the rock. Okay, during the mm, dynamic, you can have the orientation of new grains and subgrains parallel to the foliation because it is the minimum energy um, geometry for the crystallization. So they grow in in the direction of elongation, the, and they are more or less uh, conditioned by the strain field. Oh, sometimes it is tricky because in the rock kind of mimetic growth. So you have some folds and some static minerals grow above previous minerals, mimicking the fold or the granulation. But usually these new minerals show no Undulus extinction, so you can detect easily that they are growth above a previous structure, but they are reinforcing the geometry of this one, but is a particular case. Okay. Oh, the foliation useful to recognize tectonic phases in the field because, for example, the folds are very nice. You can see a geologist, a fold, the hinge of fold, and the foliation. But when you have a big fold, maybe with a limb of 2 kilometers and the hinge of 100 meters, in the field you find more frequently foliation and not the hinge of the folds. So the foliation is very constant and uh, affordable structure to work on. And usually the intersection between foliation and the bedding plane highlight the intersection lineation that is parallel to the fault axis. Maybe you have erosion here, mountains, there is erosion, you cannot see the hinge, but looking at it and looking at the intersection between the bedding and foliation plane, you can detect the fault axis, intersection lineation. And of course, during deformation, the rock usually are deposited in sediments, are buried during deformation, reach a maximum pressure and temperature, and come back to the surface. So they have a long history of deformation, and this deformation is accompanied by mineralization of the minerals and by deformation. And you can several phases of deformation in the rocks. Usually could be 4, 5, 6, 700, 7, phases of deformation. But in the rock, you are able to recognize only 2 or 3, maximum 4 phases of deformation because each deformation try to rise the previous one. So it's not to reconstruct the overall history of the rock, but best the exhumation path of the rock, part of the history. So usually the first tectonic event is characterized by one folds, means folds, D means deformation, S means surface foliation, uh, S0 is a bedding, S1 is the first foliation, S2 the second foliation, and so on. So you have to recognize the occurrence of polyphase deformation. In this case, you have bedding folded and the development of S1 foliation during in this case, in this you have a second folding. So the first fold hinge is folded by a second fold. So the first one foliation, S1 foliation, is folded, and the new one developed, that is an S2 foliation. This should be a crown, of course. Mm. So this is cleavage plane, and the microlithon, you can observe it's S1 foliation, and so on. You can deform also some other times this kind of. This is another example from is Pasquier, is bedding, deformed isoclinar very tight flow. It's a S1 foliation, a D2 foliation. You can shorten in this direction, develop a fold like this with a cannulation cleavage. Uh, Another deformation could be deform the S2 foliation in this way with an S3 foliation. So process is will be very very complex. Okay, with the thin section with the layers in quartz or in chlorite. What do you see in this picture? What you can see looking at this thin section? Okay, S1, S1, where? Maybe this. Yeah. This indicate. Okay, this fold. Okay, this is budding. So the change in composition between the white stuff and the green stuff is due to bedding, original bedding, okay? But is only bedding or there is a but okay, if I give a look to this part, we can see minerals elongated in this way. So there is also foliation parallel to the bedding. This foliation is maybe the S1, the first tectonic event. Then this foliation is folded together with the bedding, and so this is a second phase. Okay, you can development on application only in the more part, in the hinge of the fold, here, here, here. This gradational granulation cleavage. The transition from microlithons and the cleavage is gradational one. So, and you can detect the metamorphic condition of superfoliation studying the minerals growing here, maybe white mica, chlorite, quartz, and probably nothing is happening in this S2 foliation. Only rotation of the previous mineral, maybe some dissolution, some solution transfer because of the black stuff. No, grow. So probably decreasing in temperature between the F1 fold and the F2 folds, because here you can develop the mineral, deform the grains. In this way, the shortening is not so much because the angle of the limb is quite, so not much strain. And no a strong foliation developed only in the hinge zone, but not in the limb. So the formation with less strain in decreasing temperature condition. Okay, from the Northern Apennine is the place of original bedding. These are microfossils. Is the bedding folded. This is the axial plain foliation. It is a grained complex. Okay, the sampling strategy, or when you have some several deformation phases superposed, it to took samples to all in this. Prova, prova, prova. Prova. No. Maybe. No? Okay. 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 So the sample strategy is like this. If you have a foliation folded like this, you can observe a difference in composition between this layer and this one. This probably original bedding difference. But if you give a look to the hinge zone here, uh, it appears too much smooth. And probably there is a foliation parallel to the bedding that has been folded. How to be sure of this? I need to take a sample from the hinge, from here or here, and to observe in sync action. Because if there is a foliation, you can see clearly in sync action the foliation parallel to the bedding. So you can say that is an F2 fold. If you take a section here in the limb or here, you cannot decide because on the limb as bedding foliation S1 and S2 could be parallel, so you cannot decide. But in the hinged zone, the the S1 foliation became at a high angle with S2 foliation, and you can detect the crenulation cleavage. But you need to take a sample in this part, in the hinged zone. Okay. This is a movie from Fossen showing the development of 4 foliations. This is very simple, but you start, sorry, you start with an S1 foliation has been followed by an S2 foliation, the S2 foliation by an S3. S3 is further shortened by an S4 foliation. There's much number of foliation that we can observe in a rock. I have never seen 5 foliation in the same rocks. And sometimes the older foliation is preserved also only in microlithons or inside the porphyroblast that catch the former foliation. Okay. Here's some example of foliation is already seen. In this picture, you can see a crenulation cleavage with an older foliation here, a fine grain foliation with a spaced crenulation cleavage, of course, with a little bit complication by this stiff layer that causes a deflection of the foliation. In this case, you can see an older foliation and a new foliation, but we are not sure that is an S1 foliation or an S2 transposed by tectonic foliation. So sometimes it is better to speak about SP foliation, principal foliation, and SP plus 1 foliation, because until you can see the relation of the older foliation with bedding to be sure that is the first foliation. Okay. This is a classic an example of crenulation cleavage in with the 2 deformation. You can see here the bedding, the foliation that is more or less parallel to bedding. So we are in the limb of isoclinal folds. And then at a high angle degrees, a space of the crenulation cleavage that is well visible in this part. So in this case, you see the bedding, the S1, S2, and you can put the number to the foliation. Okay. Have you some question about the foliations? Maybe you are much more familiar with this topic. Okay. So I go ahead with porphyroblast. Porphyroblast. So after that we can observe some scene section maybe. Okay. Okay, the porphyroblasts are very useful for structural geology and also for petrology. So we will start to say what is a porphyroblast and the difference between porphyroblast and porphyroclast, because usually we made a lot of confusion in between the 2 terms. And moreover, the relation among porphyroblast and tectonic events. Okay, a porphyroblast a relative large single crystal which is formed by metamorphic growth in a more fine-grained matrix. Usually should be nearly 10 times more bigger than the matrix. You can see a layer of mica, a layer of quartz, a layer of mica and quartz, mica and opaque minerals, and this should be a garnet, for example, is much more larger than the minerals in the matrix, so due to metamorphic growth. So it is a perfect porphyroblast. You can see here some porphyroblast along the main central thrust zone in the Mugu Karnali in western Nepal. The garnet is very big, you can observe here. And porphyroblasts are very useful because they can help to reconstruct the tectonic metamorphic history of a rock. They contain inclusion that help to infer the relationship between blastasis and deformation. Um, and sometimes you have the inclusion in the porphyroblast and no longer in the matrix due to transposition of or deformation. So inside the porphyroblast, you can find information of the older history of the rock. Could be used as kinematic indicators, such as snowball garnet, for example. Moreover, their zoning can be used to infer the PTT history. Uh, some people say that garnet is the black box of metamorphism because it contains all the information of the history. In the Alps, there are, but also in the Himalayas, there are garnet with a rim developed during Himalayan alpine orogeny, and the inner part of the core developed during Variscan or Cambrian orogeny. So you can see two orogenies in the single big garnet. So it's very important to look at this feature. The most common porphyroblasts are andalusite, kyanite, sillimanite, sterolite, garnet, chloritoid, biotite. In metabasites, you have amphibole, pyroxene, epidot, depend on the chemistry of the rocks and of the kind of rock. Okay, the main difference between porphyroblast and porphyroclast. Yesterday, we spoke about porphyroclast in the mylonite. Porphyroclast are single crystal of a size exceeding the mean grain size in surrounding matrix and inferred to represent a remnant of an originally coarse-grained rock. Porphyroclasts are common in mylonites. The porphyroblast is a single crystal of a diameter exceeding the surrounding matrix and inferred to have grown in a solidified rocks in the response to change metamorphic condition. Okay, so the difference is a relict. The porphyroclast is a relict of a big crystal after deformation, especially in mylonite. A porphyroblast is due to metamorphic growth during the metamorphism. Okay. Okay, porphyroblast can show a complex pattern that may be not visible in the other part of the rock. So for example, you have an S1 foliation, an S2 crenulation cleavage. After that, you have the static growth of a porphyroclast. Then deformation continues, the deformation that caused the S2 foliation, the crenulation cleavage. So this part, the external part of porphyroclast is completely transposed. You can observe only one continuous foliation, whereas inside the porphyroclast you can see a picture of the old history because the porphyroclast is hard and preserve the deformation, the old deformation inside that is no longer deformed by the continuing S2 deformation. So I can give a look to the S1 foliation or to the first stage of the S1 foliation to detect PT condition or to date, for example, white micas by geochronology. So you can date this foliation, this one, the other one, and so on. Okay, in metamorphic rocks, the size and distribution of porphyroblasts is due to amount of nucleation sites and the growth rate. So if you have a few nucleation sites and big growth rate, you have a few big porphyroblasts. If you have a lot of nucleation sites and a slow growth rate, you have dozen on thousand of small porphyroclasts. In this case, each porphyroblast catch only a small part of metamorphic and tectonic history. In this case, the porphyroclast record a long history of deformation and metamorphism. So this is more or less the same concept. In this case, you have a rotated garnet, so small nucleation sites, big growth, and the growth during deformation. You can see the internal foliation has been rotated, as we saw yesterday, due to the dextral sense of shear. Okay. Just a quick look to the terminology. it is useful to distinguish in between external foliation, the foliation outside the porphyroblast, and the foliation inside the porphyroblast. Because if there is a continuity between external and internal one, or discontinuity, the situation is different and the interpretation is different. This part of the matrix that is protected by the hardness of the porphyroblast is called the strain shadow. And this part where the formation is concentrated is called the strain cap. These are cleavage domain, microletons, as you know. In the internal foliation, you can see a trace of the foliation like this, another foliation like this, with a sharp angle that is called the truncation plane. Okay. Why we need to give a look at the inclusion in the porphyroblast? Inclusion pattern can testify all the deformation events, all the deformation, folds, maybe shearing, but it is difficult. Inclusion of minerals is no longer present in the matrix. Moreover, the relationship between inclusion pattern and the external matrix can help to understand the timing of growth versus tectonic history. You can see if porphyroblasts grow before the formation, during the formation, or after the formation. And some inclusion in the porphyroblast are useful to um, to gain datation, absolute datation with geochronology. For example, monazite, zircon, allanite, they are frequently included in porphyroblast and can be used for uranium, lead, or thorium datings. Yeah, this picture came from Gandaki, Greater Himalayan sequence, the upper part. You can see a porphyroblast of garnet with inclusion in the core and a free rim of inclusion. So there is a double growth of this porphyroblast. This probably during the formation, and this mm, in a timing of no deformation, and the rim grows mostly free of inclusion. So you can detect a different PT history from the inner part to the core. And then this garnet is inside this foliation marked by biotite and quartz. So we can also detect the relation between this porphyroblast and the main tectonic foliation in the rock. But these minerals inside the core of the garnet are no more present in the matrix. So the only record of the early stage is inside the porphyroblast. Sometimes you have a folded inclusion pattern. This is a paragneiss from northwestern Nepal. This is a big garnet with a folded inclusion pattern like this. That is quartz, ilmenite, biotite, and they highlight a folding. So there is a foliation that is being folded, then the growth of the porphyroclast, so we can gain some information. There is also staurolite inside this garnet, these yellow crystals. Okay, another example of folded inclusion pattern in a garnet. Okay, okay, we can go ahead a little bit. We sometimes we have some skeletal porphyroblast, such as this skeletal garnet. It is not able to develop very well a shape because of the lacking of ingredient to build up the garnet. Maybe too much quartz rich layers, low aluminum layers. So the garnet grow only along the mica rich layer where they can use aluminum, magnesium, and so on to build up the lattice of the garnet, but it found no good materials in the quartz rich layers. So the shape is skeletal, not hyoidal. It's not the effect of deformation, but of the lacking of ingredients to build up this mineral. This is another example of skeletal garnet. Okay, and one of the most useful use of the porphyroblast from structural geology is the classification of porphyroblast with respect to the tectonic foliation. You can have several tectonic foliation in the rock, and the rock underwent also metamorphism, so the growth of minerals and porphyroblast. So you can distinguish pre-tectonic porphyroblast with the growth before tectonic foliation, intertectonic, the porphyroblast that grow after one deformation and before another deformation. Useful are also syntectonic porphyroblasts that grow during the rotation due to shearing of the external foliation, or during the growth of folds is the same, and post-tectonic crystals that grow after all the deformation happened. Okay, in this case, you can observe defoliation that wrap around the pretectonic porphyroclast. You have deformation outside that are not represented inside the garden, inside the porphyroblast. In this case, you can observe strain shadow because you have a hard porphyroblast and the foliation wrap around, and you can observe strain shadow here. For intertectonic porphyroblast, you have to develop the one foliation, first one foliation, then the growth of porphyroblast, that is static growth above the first foliation. Then there is the growth of so first foliation, the growth of the porphyroblast. Another second phase foliation started to grow, wrapping around the porphyroblast. So inside the porphyroblast, you can observe the older foliation may be folded and an external foliation, but there is no continuity by the external foliation as the internal one. There is a sharp angle in between the two. So we are sure that we are in the intertectonic porphyroblast. In syntectonic porphyroclast, you can observe the growth of S-shape foliation like snowball garnet and so on. But the most important thing is that you can observe a continuity in between the external foliation and the internal foliation. So this link could help to classify the porphyroblast as a syntectonic foliation. The post-tectonic foliation are very common in a static recrystallization due to the intrusion of plutons. So you have the formation in the country rocks and the growth of static minerals above the foliation, the tectonic foliation, the folds. It is like to put a glass on the rock. Just you see what there is behind with no interaction between the porphyroclast and the the microscope is not working there, so we can just continue to. Okay. Is that okay? There is some issues. That's why. Okay. Is it possible to go? No, because it's not working. We don't know why. Okay. So we can just continue there. Okay. Okay. So we will not go to the geology department because the microscopy is not working. So we will continue by sliding, by the slides. Okay, we will discuss a little bit more with the picture. Sorry. Okay, pretectonic porphyroglasts are very not so common in metamorphic rocks, and they are often related to a static metamorphic event, maybe contact metamorphism, later involved in the formation event. Inclusion are sometimes present, but they are often not aligned in a random way. Okay. Oh, this does not mean that all the porphyroblasts with non-oriented inclusion or without inclusion are pretectonic. It depends on the sample in section cutting, poor orientation in section orthogonal to the elongation axis, and also to the cutting effect of the minerals. For example, if I go back to this garnet, When I take thin section, I have the garnet. If I am lucky, I can cut the garnet through the central part and can observe the inner foliation and the outer rim-free foliation. But if I cut in the external part, I can observe a smaller garnet with no inclusion because I have not cut through the central part, but only close to the border. So be careful in this section because this effect is very important, especially with big garnet. If you have a lot of garnet, you cut the thin section, and if you are lucky, few garnet are cut along the central part, but the most close to the border, to the rim, so with no inclusion, with no structure. But in this case, there could be post-tectonic, intertectonic. The lacking of inclusion is not a diagnostic of the relation with the foliation. Okay, this old movie from Pasquier, made by his hands with canvas software. You can see the random foliation, the growth of porphyroblast may be due to contact metamorphism, then oops, the phase of deformation. So the porphyroblast is wrapped around the base of the deformation, but inclusion inside random. But it's very not common situation. I never seen this pretectonic porphyroblast. Okay, in this old picture by Alan Spry in 1969, he made the first classification of porphyroblast, and it was very useful. So, pre-tectonic porphyroclast, pre-kinematic crystal. Uh, but when you use the term pre-kinematic or pre-tectonic, you must refer to which phase of deformation you are dealing with, because in the rocks you have different deformation phases, so you have to specify which deformation you are referring. A pre-kinematic crystal show a bend in the crystal with ondulous extinction, so the crystal is deformed. Defoliation wrapped around the porphyroblast. You can develop the pressure shadows, such as the one around the very common pyrite crystal. You have kink band, because the crystal is previous to deformation, so it is deformed. You can observe microbudinage, such as the tourmalines that you observed yesterday. Deformation twins, like this, as a mechanism of deformation, for example. This is one of the very few cases of pretectonic cordierite in in a pelite. So the cordierite is due to high temperature, low pressure metamorphism close to a granite intruding these metapelites. So you have this mm, large tectonic of tectonic porphyroblast of cordierite, and then the growth of foliation due to a small deformation, because you can see the foliation is not so well developed. The grain size is very low, so the formation is not so strong. And in this case, you can observe the pretectonic cordierite. If the formation increases and the shortening increases, probably cordierite is deformed, transformed in other minerals, and you lose the trace of this pretectonic porphyroblast. Okay, the other simple case of porphyroblast is a post-tectonic porphyroblast. So means you have all the deformation history of the rock. Deformation stopped at a certain time, or the rock was cooled down, so impossible to record other deformation. And then you have the growth of static minerals. Or, for example, you stop the formation, but the rocks remain hot, and the minerals stable in the PT condition uh, continue to grow in a static way. And so it is like if you look through this crystal, you can see the structure below, because it is just to put a glass above the thin section, so no interaction between the static growth and the previous deformation. Okay, these are other Fish are useful to recognize static post-kinematic crystal. Elischitic folds, this one. Elischitic folds means the folds that you can observe before the growth of the porphyroblast. Uh, Randomly oriented crystal like this, with no strain, so the crystal grow in different direction. This is a particular shape called the polygonal arc that is a mimetic growth of crystal. You have a previous foliation with maybe white micas, small white micas, and the new crystal adopts the same orientation of the old crystal, but with new crystal has no ondulous extinction and only grow above the foliation, but they are after the formation of this foliation. Okay. In this picture, you have the growth of chiastolite, this andalusite, a typical andalusite during contact metamorphism, typical of post-tectonic deformation. If the intrusion is after deformation, here you can see an internal folded foliation of the porphyroblast of garnet with a rim free of deformation. So this rim is post-tectonic with respect to the core. In this case, you have the replacement of a garnet, for example, by biotite or chlorite random aggregate of pseudomorph. So there is an alteration of retrograde metamorphism, and the new minerals uses the old minerals. They use the shape of a minerals, but with a completely random recrystallization. Okay, this is a good example from Pasquier and Trau of post-tectonic or static porphyroclast. You can see this porphyroclast. Below this porphyroclast, you can see the foliation from the stylon part, internal part, going outside. So it just as a small glass put on the scene section. Of course, the composition below is changed because this mineral uses the chemical element available below to grow. So only insoluble element remain to mark the older foliation. But you can see this crystal oriented in this way, this almost perpendicular, this one. So there is a static crystallization with no preferred orientation and no internal deformation, no ondulous extinction, and so on. This sample came from Antarctica, took some expedition a few years ago. This is a chlorite porphyroblast that is completely static, not easy to recognize, but it is just put above the foliation. The older foliation go through the porphyroclast with no interaction, so it is a static growth. Okay, the most interesting are the syntectonic porphyroblast. This type of porphyroblast grow during the formation phase and they represent the most common case in nature, fortunately. And the main factor controlling the growth are the finite strain, of course, the relation between growth and deformation strain rate, and the stage of progressive deformation when the porphyroblast grew. Inclusion patterns are generally curved with sigmoidal or spiral geometry. This geometry, for most structural geologists indicate syntectonic porphyroblast can rotate during deformation because until maybe 10 years ago, 15 years ago, there was a school of thinking in Australia with some geologists think that porphyroblasts do not rotate at all. It is the overall rock that rotate, but not the porphyroblast. It's a strange kind of view, but they agree only with the noble garnet. But for the other porphyroblasts, they try to find a different explanation. Maybe one deformation in this direction, the other one in this direction, the other one. So several deformation in perpendicular direction make the same shape and demonstrated that in some cases it is possible to develop the same geometries that we usually explain by rotation in different way, but now it is almost completely abandoned, this line of thinking. Okay, if curved inclusion are due to all the folds, they are referred to elicitic fold. Spiral when there is a rotation, elicitic when the porphyroblast take a picture of the old folds. Okay, so just a small difference in name. Okay, this is an example of syntectonic porphyroblast. So here you have two deformation phases. When I say syntectonic porphyroblast, to which deformation phases I refer? To the first one or to the second? Think about a little bit. I use one. Developments of an S1 creation, S creation, that will be called S1 due to demand visual deformation. They will remove new folds. Ah, sorry. Thanks. Okay, then uh, one, two, and three. So in the second moment, there is the growth of the porphyroblast. Yes or not? Mm. Sure. Uh, you can you start to deform this foliation in this way. So you make ondulation of this foliation, and then the growth of the porphyroblast. So inside the porphyroblast, you have the first stages of the formation of the S2 foliation. Of course, the first part, the inner part, is less deformed. Then there is a growth of porphyroclast when strain increases. So towards the boundary, you have much more developed folds. Then you continue to deform. Here you have only this kind of fissure, and the external foliation is more or less completely folded with maybe cleavage domains, microlithons, and so on. So this porphyroblast, sorry, let me confusion several times, is syntectonic with respect to the first one or to the second deformation? To the second one, because it starts to grow during the first increment of deformation, then stopped and the formation continued, but it is seen S2 foliation or seen D2 deformation. Okay, and what is the relation between the porphyroblast and the S1 foliation? Not syntectonic, not pretectonic, post, because you have the development first of the foliation, then the deformation of this foliation, the growth of the porphyroblast. So this porphyroblast is also post D1 or S1 foliation, because the growth is after. Mm. So when you have several deformation phases, you you can refer the growth of the porphyroblast with the different phases. So when I say syntectonic porphyroblast, it is not a complete information, because I must specify that it is syntectonic with respect to the second deformation phases, but with respect to the D1 deformation, it is post-tectonic. So in this way, I completely described the growth of this porphyroblast, sorry. And you can also, maybe this could be albite. You can use also a kind of a diagram like this. You can put here D1 deformation, here D2 deformation, and here different minerals that you find in the rock. Maybe quartz, albite, white mica, garnet. In this case, if this is the D1 deformation, D2 deformation, I don't know the absolute value of this timing, but it is relative growth. I found the albite is post D1. So the albite I put in this condition here up to more or less here. So in this way, I say graphically that albite is post D1 and sin D2 deformation. Of course, deformation is not a single moment, but should be maybe 5, 10 million years. So, for example, if you have a quartz growing here and quartz growing here, you have put quartz all over the one and the two. For example, white mica, the same should show a growth during the one and the two. Garnet maybe should grow only between the one and the two. I put a line like this. So this is a way to describe the relation between the growth of a porphyroblast and the tectonic foliation. It's important. It was very used in the past. Now it is a little bit lost, but it's very useful. The duration of the deformation phases. Have you an idea what is the duration of deformation in the neurogenic belt, more or less? How many millions? 1, 15, 20? Not 100, okay. For example, the Himalayas collided 60 million years ago. So you have several deformation phases. Usually, for example, in the Northern Apennine, people dated just in the 80s deformation phases along the different foliation in metamorphic rocks. And well, maybe the duration is 4, 5, 6 million years from one phase to another, more or less, just to have an idea. Uh, the shear zone we dated in the Argentera Massif, the Estelvarisca shear zone, we dated by white micas and monazite, that is phosphate of cerium, lanthanum, and so on. During the duration of the shear zone is nearly 25, 30 million years. So but it is a very huge shear zone running for 1,000 kilometers with a strong displacement. The duration of maybe South Tibetan detachment would be from 30, 31 up to 17 million years. It depends on the places on the Himalayas. So the dating by different methods. The higher Himalayan discontinuity in the middle part of the Great Himalayan sequence has been dated in several places in between 27 and 70 million years. So 10 million years of shearing. So more or less, just to have an idea of the order of magnitude of these processes. Okay, we come back to the porphyroblast. Oh, this is a beautiful example of a synkinematic crystal. This is a garnet. You can see the internal foliation deformed in this way. This means that the rotation is much higher than 90 degrees, maybe 120, 110 degrees. And to be sure, this is from a nice book of Yardley, old book, but very nice, the Atlas of Metamorphic and the Metamorphic rocks and their textures. Are beautiful images. And in this case, it is a syntectonic garnet, but we should be sure that the internal foliation is continuous to external one. Here we can see a little bit continuity, but not so much. In any case, this is an example that in the book has been reported as a syntectonic crystal. There is the growth of a crystal contemporaneous with the rotation due to shearing. Okay, this is the growth of thin kinematic crystal, usually garnet, most classical. There is a foliation, the initial growth of a garnet, the growth of the garnet and the starting of shearing the left sense, the growth increase, so the shearing, the foliation is deflected and rotated. In this way, you develop the rotation of internal foliation during the growth of the crystal. So this is a very nice example of a synkinematic crystal. But if you look to the external foliation that enter in the porphyroblast, is rotated and come out in this part in a continuous way without interruption. Is a very important feature for the syntectonic porphyroblast. This example that I showed you yesterday, growth and rotation, dextral rotation, clockwise rotation means dextral shearing, because all the things rotate in the same way of the shear sense, especially in simple shear. An example of the example of the garnet with the rotation of 90 degrees, because from here to here is 90 degrees, but the external foliation come inside the garnet with no solution of continuity and come out with the same orientation. Of course, the composition is different because the garnet to grow needs to use the minerals no? In this area, but the foliation is the same. Okay, this is a staurolite porphyroblast from this unit in Antarctica. Is a pressure unit in the Antarctic craton. What do you think about this staurolite porphyroblast? Is it syntectonic, pretectonic, post-tectonic? Syntectonic. Okay. I like this. Syntectonic is a good answer because there is a rotated defoliation here, but there is continuity with the external part. In this portion, it is a little bit less evident, but should be continuous. And the rotation is sinistral or dextral. Sinistral. I, I come back. In this case, we have a dextral rotation, and you can see this kind of shape. So if you go ahead, it's a little bit different. It's opposite because the foliation like this. So the rotation is in this sense. So the growth of this starolite porphyroblast is during sinistral shearing in this thin section. Here the okay. Oh, we are in Sardinia, just close to the East Variscan shear zone, in a place where there is a growth of garnet, biotite, staurolite, and a few hundred meters away also kyanite. So in Barrovian metamorphism, this picture is one polarized. We can observe this euhedral crystal of staurolite. Mm. Here there is a foliation. Here, the foliation come inside and go outside here. But you can see that there is some deformation affecting this porphyroblast because there is some strange shadow here. And here the foliation converge in this direction or merge in this other direction. So in this case, we can say that the growth is syntectonic with respect to the development of this foliation. Uh, the, the porphyroblast grow during the first stage of deformation, then crystallized. Deformation go ahead, making strain caps here, strain shadow, and this shape. Okay, so this is a syntectonic porphyroblast. Obviously, we cannot saying about shearing in this section. There is some shearing, but could be evident, start to be evident by this SC plane, but very few example. We needed to move towards the shear zone, the regional shear zone, to observe much more kinematic indicators. It's just the beginning. Okay, we come back to the Himalayas with this staurolite porphyroblast that has been interpreted by Iaccarino that made the PhD thesis in Western Nepal in Mukarnali. This is a syntectonic porphyroblast for the same reason. External foliation inside the porphyroblast. Let's go in this direction and come outside. So in this case, the rotation is dextral or sinistral. Dextral one. Okay. So the top up to the right. Okay. There are beautiful minerals in the rocks in the Himalayas. Okay, we are in the northern Apennines with the crystal, with mica schist, with the crystal of kyanite. Here and here. This is chloritoid. So condition of maybe high pressure metamorphism during the subduction. And this crystal has been interpreted as syntectonic porphyroblast. Do you agree with this interpretation? Hmm. Not for the chloritoid. Why? Okay, you can see a crystal recanite here, little bit wrapped around by this foliation. Another crystal here. You have a foliation outside and inside. It's not an easy example. They look like maybe post-tectonic porphyroblast. Yeah? Uh, Probably you need to observe all this in section. Probably you are mm, in a part, in a less deformed part. But probably better interpretation is post-tectonic crystal because for what I know, for what I see in this picture, there is an external foliation go inside and going outside with no big interaction here. Here there is a deflection of the foliation, but it is also outside. This is, I am not sure this is a strain cap. Maybe there is a static growth of this crystal up to this here, just in this position. So probably from this picture, it is better to put post-tectonic porphyroblast. Maybe an error in the caption. Okay. Sometimes you can observe a foliation like this. You have a porphyroblast with an internal foliation in continuity with an external foliation here and an external foliation here. So what is the right interpretation? The axial simple shear, pure shear, sinistral simple shear. In this picture, Pasquier made the movie and show that starting with different position of the foliation with respect to the porphyroblast, we can obtain the same geometry with different mechanism of deformation. So you can observe also external, internal, external, here, 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 by distal simple shear, pure shear, and sinistral simple shear. So uh, we should be careful to interpret the sense of shear only using one porphyroblast like this. Probably and surely in this rock there are several evidence of distal rotation, but with only one an example, it's dangerous because if the original situation is with an horizontal foliation, vertical foliation, you can reach the same final result both by distal and sinistral simple shear. So be careful to use only one porphyroblast. It is better to use all the possible kinematic indicators because this final shape in this case, there is a little bit difference because for sinistral simple shear, this foliation remain here to be um, parallel or to the horizontal plane should be a very strong deformation or a component of pure shear. But in any case, so it is possible to obtain this final feature with different deformations. Okay. Okay, so since we have different deformation phases, we we can found very often also in intertectonic porphyroblast. So intertectonic porphyroblast means porphyroblasts that have grown over a tectonic foliation and are surrounded and wrapped around by new foliation with no records within the porphyroblast. Okay? The S internal foliation is straight and often discontinuous with respect to external foliation. Here we have an example of staurolite crystal here, staurolite crystal here. This is a garnet, this is a small garnet, this is an external foliation made by white mica, and quartz is white mica with some folds. Some quartz are crystallized here, and inside the porphyroblast, you can observe a foliation here, marked by ilmenite and so on. Also here, a strong foliation, graphitic materials and ilmenite. So this is a perfect case of intertectonic porphyroblast. You have the development of internal, what we can see as internal foliation. Okay, so first of all, you have to develop a foliation like this. Mm. Then you have the static growth of starolite, like this, maybe. Facciamola, ok, different. Okay, starolite like this. So you have the external foliation, the internal foliation in continuity. So in this case, the starolite is post-tectonic with respect to the D1 deformation, giving rise to S1 foliation. Okay. After that, you have to make a Boudin of this starolite porphyroclast. So you have to shorten in this direction and to stretch in this direction, Z and X. So this porphyroclast is very strong. Okay. Is broken in two parts. The internal foliation is preserved. Internal foliation. The external foliation wrap around the porphyroblast and is folded in between the space of the Boudin. This kind of fold are named scar folds. They are common in boudinage of material. And what happened inside? The foliation is folded, and the fluid depositate quartz. There are quartz inside, the crystal of quartz, that is recrystallized. They show recrystallization because you can see, for example, the boundary are deformed in amoeboidal shape. So probably this deformation happened at a high temperature because you can see something similar to grain boundary migration because the boundaries of quartz are not the classical like this, but they are with amoeboid shape. So there is a growth of crystal and the recrystallization inside, and the high temperature is in agreement with the pressure and temperature. So this porphyroblast is starolite porphyroblast is after the one, but starolite is previous D2 deformation. So it is intertectonic. The growth is after S1 foliation, but before the development of S2 foliation. Probably this foliation is an S2 with a transposition of the NS1 foliation, because in this since action we can never observe the minerals of S1 foliation, only inside the starolite or garnet. And okay, this also, the mechanism of the formation of quartz is also a good indication of the temperature, because could be mainly grain boundary migration, maybe high temperature. The last deformation mechanism is increasing temperature, and this is in agreement with the thermometers used by garnet, starolite, biotite, white mica, the phengite content in white mica, because more or less the temperature are nearly around, say, 650 degrees of temperature of the formation, and the pressure is around 13 kilobars during the second phase deformation. There are some other important things in this part of the belt, because of course here you have not good minerals because they are used by starolite, but in the same outcrops there are also albite porphyroblast, which are inside garnet, quartz, biotite, white mica. And in this case, we detected all the mineralogy to assess the D1 condition of the formation. And the D1 condition were more or less 670, I don't remember very well the temperature, but the pressure was larger than 13, 15 kilobars. So this foliation was formed during the collisional stage. The second one, and the growth of starolite, the second garnet, and so on, developed during the exhumation of these metamorphic rocks. And the exhumation was linked to a shear zone, a wide shear zone, as the Est-Variscan shear zone. So we used the okay. Too strong. Okay, great. Thank you. Uh, so using the porphyroblast, we can assess the growth history between porphyroclast and the formation phases, giving a look to the deformation mechanism, also an estimation of the temperature of deformation, and using the mineral inside some porphyroblasts, such as albite, that is very common, or oligoclase, also the PT condition of these minerals. I use again, very strong. And we use it also, I will show you in the next days. Here you have mica, white mica inside the porphyroblast, and the white micas outside the porphyroblast. This is an S2 mica, this is an S1 mica. The ages, argon ages, 40, 40, 39, give information about 340 million years. The foliation outside is around 315, 320 million years. So if you use correctly all the information inside the porphyroblast, outside the porphyroblast, you can have a complete deformation history of the rock. Of course, not only by one since action. You have to use several since action, a lot of work in the field, mapping, structural analysis, because it's not easy to go in a place to take since action and to reveal all the formation history. This work uh, lasted several years, of course. Also because geochronology is very expensive, and you have to spend a lot of money to make detections. Also, petrology, you can use electronic microprobe to make the map of the minerals. to estimate the temperature. But in this way, starting from the porphyroblast and the foliation, you can gain information about the composition of the first foliation, the pressure and temperature, the age, and if you work at a larger scale, also give a look at the deformation that is characterized by shearing in a ductile condition, shearing and folding. There is a repartition of the formation in between shearing and folding. So these porphyroblasts are very useful. Okay. So the correct interpretation of the relation between porphyroblasts and tectonic and foliation is fundamental to go in the right direction, because if you are wrong in the interpretation, you completely go outside the right interpretation. Okay, this is another example of intertectonic porphyroblast. This is a biotite from Pasquier and Trau. Mechanism is the same, the growth of S1 foliation, the growth of biotite with a foliation, internal foliation straight one, and the outside foliation has been deformed. So outside there is a cause of deformation, a mass of deformation with folds, but inside the foliation remains straight because the porphyroblast protect the internal foliation to be deformed by the second phase deformation. So this is a classical case of post D1, pre D2, D2 deformation, so intertectonic porphyroblast. Okay, this is another example of intertectonic garnet. You have an internal foliation, but there is no continuity between this foliation and the external one. So it is absolutely not a syntectonic porphyroblast, but intertectonic. There is the growth of S1 foliation, then the porphyroblast. After that, further shortening, giving rise to the second phase folding and foliation, and the S1 foliation is completely preserved inside the porphyroblast, that is intertectonic, before V2 and after V1. This is just a particular of another intertectonic Gardner porphyroblast from Western Nepal, in the greater Himalayan sequence. You can clearly observe a garnet here, internal foliation, and the truncation of the internal foliation with respect to the external one, made by biotite, white mica, maybe sillimanite sometimes, but there is a completely disagreement in between the two foliation. So is sure this porphyroblast is sure pre the pre this foliation. Okay, this is another intertectonic garnet porphyroblast for the main central structure in Uttarakhand, just not far from here, that we studied several years ago, in the main central thrust zone, because you know there is an inverted metamorphism with kyanite above, then starolite, garnet, biotite, going to the lower part, to the lesser Himalaya. And also in this case, you have an internal foliation, the growth of porphyroblast, and the porphyroblast is wrapped around by external foliation, and there is no continuity by the internal one and the external one. So maybe in some places we can suggest a continuation towards the external part, but there is a completely truncation of this foliation. So to be sure, we must interpret this porphyroblast as intertectonic after this foliation and before this external foliation. Okay. Okay, this is just the previous example of intertectonic biotite porphyroblast in the book of Pasquier. It's quite clear. The internal foliation is a straight one. Yes. The external foliation is folded in a very complex way because of the disturbance of this porphyroblast. So biotite is after the internal foliation and before the external one. We are also in Western Nepal, higher Himalayan crystalline expedition of 25 years ago. We are close to the main central thrust, but in the higher Himalayan crystalline, this garnet has a rotated foliation inside. So one could think, oh, it could be syntectonic, but the internal foliation is not in continuity with the external one. There is a sharp discontinuity in between the two. So this garnet is intertectonic. Do you agree? Okay. Here's just an example similar to this one from the same kind of rocks, a few dozen meters. We can see the boudinage of the staurolite crystal, a lot of garnet crystal inside the staurolite, also some biotite here, and maybe some deformation inside the rim of the porphyroblast. This means that staurolite has a complex growth, not only after the one a previous D2, but probably there are some crystals that show a growth during the first stage of the formation of the S1 foliation. So the growth of the staurolite is a little bit longer with respect to the previous picture, but um, the overall structure is nearly the same. Uh, you can observe also some kyanite here and some garnet outside. Of course, this garnet and this garnet has different composition. This is in agreement with a much more deeper condition of deformation, and this is in agreement with more or less the same temperature, but uh, low in pressure, or at least 5-6 kilobars. Because during the second phase deformation, the rocks were exhumed to the surface by shearing and compression, transpression. So there was an extrusion towards the surface during this deformation. Oh, another kind of strange structure as a millipede microstructure, just observed by Bell and Rubenak in the 1980. Bell was one of the most strongest people who believe that the porphyroblast do not rotate. But at the end, it was almost convinced, I think. Millipede structure are very strange because you can observe internal foliation that they go in this direction. These go in this direction, this one, and this one. So this is very strange to explain. So one possible explanation is this one proposed by Pasquier. You have a vertical foliation, a growth of porphyroblast of maybe albite, this one, a D2 deformation with vertical compression. The foliation is deformed in this way. The formation continues. So this kind of foliation go to the right, this go to the left, the same here. And the final picture is this one, similar to the porphyroblast that we can observe in this thin section. It is quite strange, but it is the only explanation we found for this millipede structure. And all the people agree to this, or never one studied a lot of this problem because and this is more or less a picture made by a movie made by Basquiat to explain this kind of a strange picture. sometimes we should be careful because we have inclusion in porphyroblasts that are not due to deformation or superposed deformation, but they are determined by crystallographic orientation. For example, Andalusite and variety called chiastolite show inclusion during along these planes that are due to the crystallography of the Andalusite, or some inclusion parallel to the mineral cleavage, especially in micas, white micas or biotite. And for example, in this starolite porphyroblast, there is also some kyanite inside, but you can observe this pattern of insoluble materials, ilmenite, graphite, that follow the crystallographic mm, planes of the growth of the porphyroblast. So this is a strange situation. This not means that these planes are folded, but they follow the crystallographic pattern of the crystal. Also this one, this one. So just to make not confusion. The same in this starolite in the yellow crystal, and in garnet this crystal one. The inclusion follow the crystallographic phases of the crystal with no reference to the deformation phases. The same can happen in chloritoid. This came from Tibet, close to one of the metamorphic dome in Tibet, studied by Chiara Montomoli, published in 2018. There is an increase of deformation going towards the metamorphic core of the dome in the middle part of Tibet. And this chloritoid, there is hourglass zoning, this one. It is due to the crystallography of the chloritoid and not to deformation. Okay. So you know that we can identify different metamorphic event in tectonite. We call deformation event D1, D2, D3, the folding F1, F2, F3, and so on. Foliation S1, lineation L1, L2, L3, with clear distinction between elongation lineation or stretching lineation and intersection lineation, because the meaning is totally different. Okay. And the metamorphic stages are named M1, M2, M3 because the rock passes through different stages of metamorphism and PT condition. So we need to reconstruct a tectonic metamorphic history to build up a tectonic model. Usually we use all this stuff. Okay, yeah, we can see some example of tectonic reconstruction. Here in this part you have first phase deformation giving rise to an S1 foliation, probably due to folding. This S1 foliation has been deformed by contraction in this direction by D2 deformation. So you have these microlithons with granulation inside and the cleavage domain. So you have a granulation cleavage. After that, you can produce a shortening like this. So these lines become deformed in this way, whereas these one are flattened. So this is a particular situation that came from the observation of this granulation cleavage that has been folded only in the cleavage domain. The name is selective deformation. Why it is a selective this deformation? Why the fold are only observable in this cleavage domain and not in this one? Have you an explanation? A possible explanation? Sorry. Because in the first case you have folds here and cleavage here, but all the stuff is folded. Here you can develop the folds only here and not here. It's strange, a little bit. Okay, one possible explanation is that if you have a contraction in this direction, these lines are in the field of shortening, whereas these lines are in the field of extension. So these folds are flattened and become more straight, and this one develop the folds also because there is a growth of white mica here, so much more easy to develop the D3 deformation. So I can try to make a small picture. Okay, we start from this situation. So this is the S1 foliation. It is S2 foliation. Then what happened is a contraction in this direction. Contraction means stern ellipsoid like this. Z-axis, x-axis. This is extension and this contraction. So uh, if you observe these lines, these these domain cleavage are more or less parallel to the contractional axis. So they are in the best position to be folded. Okay. And also in this part, there are also an enrichment in micas, where in this part you have more or less quartz and very few micas. So the cleavage is much more better developed in this part. But this small folded foliation is in the direction of extension. So it is flattened and extended. So these folds are not increased, but are flattened. So at the end, the final picture is beautiful for the ear, and these small folds are flattened. So in the microlithons of D3, you cannot see the F3 folds that are developed only in the cleavage domain of the S2 foliation. And this is called a selective crenellation cleavage because we can develop it only in these layers and not in this one because of the position of the layers with respect to the shortening. If we had the deposit, if the strain was oriented in this way, again in this way, this part should be elongated, this fold should be much more shortened. But with this orientation, this part is shortened and this elongated and flattened. But this is quite common in seed section. It is not so strange, such as millipede structure. Yeah. Mm? Uh, if the strain is very high with in this direction, hmm, if the strain is very high, you can shorten more and more this fold, but this part is remain flat because it is more or less parallel to the foliation plane of the finite strain ellipse. So it is a stable position respect to the deformation. So this part is shortened and shortened, but the one flattened and remain flat. To deform this part, you have to change the axis of deformation. And if you rotate the axis and the foliation is oblique to the elongation direction, you can deform again this foliation. But you have to rotate the deformation axis with respect to this picture. So if the D3 deformation is rotational deformation or coaxial deformation, it is possible. If it is only magari by push shear, only by push shear, the situation remain here and not change. But with the rotation, possible. Okay, this is just an example of how to describe mineral growth called blastesis. It is not the term, but it is nice for me. And to build up a deformation diagram, you can see here, for example, D1, slaty cleavage, D2, granulation. Here you can put the mineral, chlorite, garnet, sterolite, biotite, albite. And here you put the growth of porphyroblast or the minerals that you find along the foliation. Example, chlorite should be porphyroblast before the formation. So I put chlorite here. Biotite develop only during D1. So I put biotite here. Garnet is intertectonic after D1, but pre D2. I put this kind of line with inflated central part to say that in this position there is a maximal growth of porphyroblast, but someone could grow also later. So the maximum growth is here, the minimum here and here. Starolite has a pre-D2 deformation and seen D2 deformation. So show both the characteristics. Biotite is seen D2 and post D2. Albite is post D2 deformation. So there are also some symbols, but more or less the significance is the same. But it is very useful to analyze the scene section before studying deformation or studying PT condition to make much more complex analysis such as isochemical pseudosection because it's very useful to understand when the minerals grow with respect to deformation because you cannot put all the minerals together to describe, for example, the deformation during D2. If you would like to detect the D2 condition of pressure and temperature, you must avoid the chlorite and garnet, and you have to use only these minerals. So when you have all the minerals in a rock, you cannot put only in the program to calculate pressure and temperature. Okay, and finally, we can observe some exercise made by old book by Bard, 1986, about a microtexture of igneous and metamorphic rocks. You can see here porphyroblast growing after a fold by maybe biotite, and the porphyroblast should be sterolite. I don't know. Okay, this is another way to represent Andalusite. Okay, sorry. The yellow one is Andalusite. To represent more or less the deformation. You can put quartz and muscovite in the lower part here, D1 and S1 deformation, D2 and S2 deformation. So you have the growth of muscovite and mica and quartz during D1 and during D2. And Andalusite is static above the folds due to M2 contact metamorphic event. So regional event M1 with quartz and muscovite, and M2 contact metamorphism with the development of static Andalusite. This is another way to represent the relationship between deformation and growth of minerals. Here's another nice picture from all the book from Alan Spry, the first book about microstructure, but it was quite nice. Here you have development of folds. You can see the folds deform fold S0, the bedding, there is a growth of S1 axial plane foliation. This porphyroblast is albite. This porphyroblast is garnet, albite, and so on. So you have the folding of bedding, the development of S1 axial plane foliation, then the growth of static albite and garnet, post-tectonic with respect to S1 foliation. Then you have a shortening, developing an S2 foliation, this one. So these minerals are wrapped around by the S2 foliation. So these minerals, albite and garnet, are pre-tectonic with respect to S2 foliation. So intertectonic in a general sense with respect to the S1 and S2 foliation. After that, you can have the development of an S3 foliation like this, holding the S2 foliation. Okay, so it is just a nice reconstruction to understand what happened. Yeah. Of course, you start from this picture and you come back in this way. Mm. But if you detect the correct relationship between the porphyroblast and the S1, S2, S3 foliation, you can unreveal all the tectonic history. So you can detect the PT condition, the tectonic condition during the development of this F1 fold, because you can observe that the thin section scale, but the fold are present also at the autograph scale, at the decametric scale, atometric scale. So they are related to maybe shortening or collision or some other things. And the growth of minerals along the S1 foliation, the static minerals, and so on. So this is a starting point to correctly interpret metamorphism and deformation history. Then you can use all the modern technique, isochemical dissection, biochronology by laser ablation, but it is very important to be sure what are you doing, what are you dating, or what are you determining the pressure and temperature, because it is important to attribute the PND condition and ages and tectonic stages to the real moment of deformation. Okay, you cannot make confusion between S1, S2, S3, or interpret the porphyroblast in different times, because the result is completely range and not in keeping with reality. Okay, so we cannot go to observe since action, but more or less, I think the most representative sample that we can observe in the since action are in the slides. So you can have a reference with a PDF if you should use this kind um, of structure of picture. And of course, the book of Pasquier and Trau is very useful for this, because Pasquier and Trau were studied with Anke Zwart, that was an expert in porphyroblast, maybe the first geologist studied porphyroblast in the 50s, in the 70s, in the Pyrenees, in the Variscan Belt. Then Pasquier and Trau used a big collection of rocks in the Netherlands, and after 10, 20 years, they write a book with a good collection of picture and a good description of picture. And so it is a very nice reference book. It was published maybe 20 years ago, but it is very, very useful. Of course, some techniques improved, but the basic knowledge of tectonic and metamorphism and porphyroblast in relation with foliation are put in the book, are very, very good, very clean, and very well understandable. The book is very well written, of course, so it's easy to read. I will give, we cannot register now, uh, but people know, but it's useful. Okay, so for today, I think is enough. Okay, thank you very much, and see you tomorrow for the third day of this very condensed course. Think about the question. If you have a question about this topic or the topic that we took yesterday, please answer. Okay. Yeah. Yeah. Oh, okay. 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 The question from your colleague is nice because I spoke about axial plane foliation that is just parallel to the axial plane and parallel to the fold axis. But in some cases, where there is a transpectional deformation, transtensional deformation, you have different timing in developing the fold and the foliation. So in some cases, you have the fold axis as transected by the foliation with small angle, maybe 10, 20, 30 degrees, because you can start to deform the layer of the rocks, the bedding, so you can develop, amplify the fold. But the foliation start only when more or less the 30% of the rock has been shortened. So if there is a rotation, you can develop the fold, then you rotate the strain axis, then you can form the foliation after 30% of shortening with transetted angle with respect to the fold axis. This has been described in the 90s in very beautiful outcrops in Scotland, attributed to transpressional deformation because you need a rotation of the strain axis. And we found also beautiful example in the Northern Apennines along the seaside with beautiful folds with one phase of deformation with the fold axis at maybe 20, 30 degrees with respect to the foliation. That is a transection. So in the so more or less the shape of the fold is here. You have the fold, the axis, and the trace of the foliation is not parallel to the fold axis, but it make an angle like this, maybe 20, 30 degrees, no more, because at the end, if you have the fold axis and the defoliation, and there is a strain and the rotation, these two lines try to intend to rotate towards the parallelism to the maximum elongation direction, and this angle is maximum this position, then diminish up to 0. So sometimes, if even if this, there is a transecting between foliation and the fold, this angle tend to disappear with increasing strain. There is also a possibility you can have axial plane foliation in the profile plane that is parallel to the fold axis, but transected along this plane. And sometimes there is also a difference in between the axial plane and the defoliation. There will be a double transecting in this plane and in this plane. But it is explained by the progressive rotation and different timing of development of the fold and with respect to the foliation. And sometimes people use this the angle of transecting to assess the rotation, the sense of shear. It's a bit dangerous, but some people do this or did this in the past. Okay. But I need the glasses. Yeah. Hmm. 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 In this case? Ah, in general case. Yeah. Yeah, yeah. Mhm. Mm. Ah. Mm. 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 Mhm. Mhm. But I don't really understand this situation. You have bedding with a vacuum foliation and S2 only the limb of the fold, only the limbs. Hmm. But are you sure that it is only bedding or there is a foliation parallel to the bedding? Hmm. Maybe this one is an S1 foliation folded and this maybe the same cleavage like this. Yeah. Mm. Because you can have some refraction of the cleavage. So maybe you have folded foliation in contemporaneous to bedding and an S2 foliation here and there with a refraction of cleavage. So the shape is a little, the attitude is a little bit different, but is in this layer much more competent. There is a rotation. Maybe you cannot develop the foliation here because maybe quartz rich layer, and here you have the mica layers and they develop the S2 foliation. You have to check the hinge of the fold. Yeah. Okay. Other question? Are you comfortable with porphyroblast foliation?
One porphyroblast, you asked that this was the porphyroblast, and in that, like the intrusions were there, sir.
Yeah.
And the bedding was like this. It was
Yeah.
going like this, and you said that it has no relation with this. So what if the firstly it was like this, and after that, sir, due to the rotation of the porphyroblast, maybe this caused these lines, and the internal ones got by the rotation, they got aligned that like this. Can this also be possible?
Uh,
Like in one of the slides, you have shown that it has no relation with this.
okay. Do you mean that at the beginning you have a rotation with a continuity of foliation from inside to outside, and only later you have a discontinuity between the foliation? Okay, yes, possible. It's possible. If you stop to rotate and continue to shorten in the same plane, you can lose the connection from internal part and external part. Yeah, yeah, yeah. Welcome. Is it all right? Okay. Other question? Okay. So thank you very much and see you tomorrow.